Right now, 3 separate streams of debris are burning up over your head. The fastest of them arrives at 59 kilometers per second every August. That stream comes off one object, and that object is 26 kilometers wide. The rock that ended the dinosaurs was somewhere between 10 and 15 kilometers across. In 1992, a circular published out of Cambridge gave that comet a date. The 14th of August, 2126, was printed as a possible impact. 8 weeks later, it was withdrawn, and the reason for that is genuinely strange. So here is the question that everything else in this story depends on. Did we prove that Comet is safe, or did we merely stop seeing the danger? Hit subscribe and tell me in the comments where you are watching from. Now let's get into it, starting with the 3 streams overhead. Part 1. The 3 clocks nobody told you were running. There are 3 separate meteor streams crossing the Earth's path at this moment. Every piece of coverage you will read compresses all 3 into one word. That compression is where the actual story gets lost, so let me separate them. The first is called the Alpha Capricornids, and its peak fell around the 30th of July. The rate is low, generally 2 to 5 meteors per hour under good conditions. Occasionally it rises to 8 or 9 during a short burst of activity. On paper that is unimpressive, and nobody plans a night outdoors around it. But the Alpha Capricornids have a reputation far out of proportion to their numbers. They are slow, and they are extraordinarily bright when they do appear. 23 kilometers per second is leisurely by the standards of this discussion. The particle spends longer in the upper air, decelerating, shedding material, glowing the entire descent. The result is a meteor that people describe as drifting rather than flashing. Deep orange, sometimes yellow, occasionally bright enough to throw a shadow. The parent of that stream is a nearly dead comet, designated 169P/NEAT. It measures about 2.3 kilometers across and barely outgasses anymore. Functionally, it is a rock carrying the history of something that used to be active. That stream is also a preview of something, and I want you to notice this. In 2010, Peter Jenniskens of the SETI Institute published a study with Jeremy Vorbayon. Vorbayon works at the Paris Observatory, and their paper ran in the Astronomical Journal. It appeared in volume 139, beginning on page 1822. The 2 of them traced that debris cloud backward through time using orbital modelling. What they found was not gradual erosion from a comet slowly wearing down. The stream came out of a single fragmentation event thousands of years in the past. That event happened roughly 4,500 to 5,000 years ago. Something near half the parent body's total mass came apart at once. That is not weathering, and it is not a slow process of erosion. What their model describes is a large comet breaking itself into pieces. Their model says the resulting cloud is still spreading and still evolving today. Earth's orbit will move deeper into its densest region over the coming centuries. Their conclusion is specific, and I label it clearly as a model prediction rather than an observation. Sometime between roughly the year 2220 and the year 2420, that shower changes. It becomes a major annual event, stronger than any annual shower currently on the calendar. Hold that idea, because a stream getting stronger is going to matter a great deal later. The second stream is called the Southern Delta Aquarids, and its peak has just passed. It reached maximum on the 29th and 30th of July this year. Arrival speed is 41 kilometers per second, roughly double the Alpha Capricornids. The idealized dark sky rate sits somewhere around 16 to 25 meteors per hour. What observers actually record in real conditions is closer to 7 or 8. Its parent is probably a comet called 96P/Machholes. I want to be honest about the word probably, because most coverage states it flatly. It is a suspected parent rather than a confirmed one, and there is a competing candidate. Mach-holes itself is one of the genuinely strange objects in the inner solar system. When astronomers took its spectrum, they found it severely depleted in cyanogen and carbon chain molecules. Almost every other comet ever measured carries those compounds in reasonable quantity. Comets that formed in the same solar nebula ought to share a broadly similar chemistry. This one does not, and that anomaly is not small. It has led to a real, published, entirely non-fringe hypothesis about the object's origin. Either it formed in a very different region of the solar system entirely, or it did not form anywhere inside this solar system at all. Stay with me, because that possibility returns in a form you will not expect. The third stream is the Perseids, and it is the reason for everything that follows. Arrival speed is 59 kilometers per second, with measurements clustering between 58 and 61. The peak falls on the night of the 12th into the 13th of August. Calculated maximum is around 14:53 universal time on the 13th. The theoretical rate is roughly 100 meters per hour under perfect conditions. The realistic dark sky figure lands somewhere between 50 and 80. This year the moon does not interfere with any of it. The 12th of August 2026 is a new moon at 0% illumination. That gives the best Perseid viewing geometry available since 2018. Let me put 59 kilometers per second into a form you can actually feel. At that speed, an object crosses the entire continental United States in roughly 80 seconds. It covers the distance between London and New York in about 94 seconds. It is moving fast enough that the air ahead of it cannot get out of the way. That failure of the atmosphere to move aside is the reason you can see anything. So there are 3 streams, 3 parent bodies, and 3 clocks running simultaneously. Each has been ticking on its own schedule for thousands of years without interruption. They all happen to sweep past our orbital position within about a fortnight of each other. That is pure coincidence, and no physical connection links any of them together. I am not going to pretend otherwise for the sake of a better story. There is one more thing about the timing this year that deserves attention. The late July peaks were badly compromised by bright moonlight. The moon was close to full during the Alpha Capricornid and Delta Aquarid maxima. Illumination sat somewhere around 98% across those nights. A bright moon does not stop meteors from arriving at all, it simply raises the background brightness of the entire sky. Fainter meteors then become effectively invisible against that raised background. You lose the great majority of what is actually arriving, which is why the Alpha Capricornids were the visible highlight of that week. Their fireballs are bright enough to punch straight through moonlight. The Delta Aquarids, being fainter on average, were largely washed out. 11 nights from now, that entire situation reverses itself completely. The moon disappears entirely from the sky for the Perseid peak, so keep the difference between those two situations in mind. Nothing about the streams themselves changes between late July and mid-August. Only the background brightness of the sky above you changes. But the Perseid parent is not like the other two in one specific respect. It is the largest object known to make repeated close passes of this planet, and the light it produces is not what almost anyone thinks it is. Part 2. Why the streak in the sky is not the object. Before the parent body can mean anything to you, you need to understand the light itself. Nearly everyone gets the physics of a meteor exactly backwards. Once you have it the right way round, every number that follows lands differently. Here is the intuitive assumption that almost everybody carries into a dark field. A rock enters the atmosphere, friction heats it up, and it burns like a match. You then see the resulting flames streak across the sky above you. That description is wrong in almost every particular, and I want to rebuild it properly. Start with the size of the object involved, because that alone surprises people. A typical Perseid, the kind producing a clean visible streak, is genuinely tiny. It sits somewhere between a grain of sand and a modest pea. Some of the brighter examples reach the size of a small pebble at most. The mass involved is frequently well under a single gram. Now put that mass at 59 kilometers per second and send it downward. Ask what happens when it meets the top of the atmosphere at 120 kilometers altitude. At that height, the air is extraordinarily thin by any everyday standard. It is thinner than what a laboratory would call a hard vacuum. But thin is not the same thing as absent, and that distinction does all the work. At 59 kilometers per second, the particle outruns the ability of air molecules to respond. They cannot flow around it, so they pile up in front of it instead. That compression forms in a thin layer, and it forms within microseconds. Compressing a gas heats it, and compressing it that violently heats it to thousands of degrees. So the grain is not burning in any sense you would recognize. It is being struck by a wall of superheated gas it created itself by arriving. The surface layer does not melt and drip away like candle wax. It vaporizes directly, atom by atom, and gets stripped into the airflow behind it. That process is called ablation, and it happens fast enough to consume the grain entirely. The whole event typically finishes within a second or two of beginning. I need you to notice the next part, because it is the piece nobody mentions. The light arriving at your eye is not coming from the grain either. That light is produced by the air surrounding the particle instead. Vaporized metal atoms leaving the particle collide with air molecules at those same absurd velocities. Those collisions knock electrons loose from the atoms they strike. What you are actually watching is a column of ionized atmosphere, tens of kilometers long. It glows as those displaced electrons recombine with the atoms they left. The streak you observe is the trail itself rather than the object making it. You are seeing the wound, and never the knife that opened it. Put all of that into plain terms for a moment. Something smaller than a raisin arrives, moving fast enough to cross a continent in 80 seconds. It punches a glowing hole in the sky 80 to 120 kilometers over your head. You get about half a second of that, and then it is gone. Now here is the relationship that reframes the entire subject, and it is not intuitive. Kinetic energy does not scale with speed in a straight line. Energy scales with the square of the speed instead, which is a different thing. Double the velocity, and you get 4 times the energy delivered. Triple the velocity, and you get 9 times the energy delivered. That single fact explains why the Perseids produce so many fireballs relative to their mass. A Perseid grain arrives at 59 kilometers per second and carries roughly 9 times the energy. The comparison is an identical grain arriving at 20 kilometers per second instead. 20 is a fairly typical asteroid encounter speed in the inner solar system. Same rock, same mass, 9 times the violence on arrival. Take that squared relationship with you into the next section. I am going to hand it back to you in a considerably less charming form. There is one further property of these particular grains that changes how the sky looks. Those particles are extremely old, and I mean that in a specific sense. The Perseid stream as a whole has been estimated at around 100,000 years in age. There is a denser and younger core inside that stream, aged around 25,000 years. The uncertainty on that core figure runs to roughly 10,000 years either way. The total mass of the stream sits somewhere in the region of 40 trillion kilograms. So consider the specific grain that produced the specific streak you saw last August. Sunlight shed it from the surface of a comet at some moment in the deep past. The ice around it warmed enough to lift it free of the nucleus entirely. It has been orbiting the sun independently and silently ever since that moment, possibly for tens of thousands of years, possibly since before agriculture existed anywhere. And it ended in your eye in half a second, 100 kilometers above your head. That is what a meteor shower actually is when you strip the poetry from it. A very old object is being slowly disassembled, and the pieces are arriving on a fixed schedule. There are two further details about that light worth knowing before we continue. The first concerns what sometimes stays behind after the streak has faded. Occasionally a bright Perseid leaves a faint glowing line hanging in the sky. That line can persist for seconds, and very occasionally for several minutes. Observers call it a persistent train, and it drifts slowly with the wind. What you are seeing is the ionized column failing to recombine immediately. Chemical reactions involving atmospheric oxygen continue emitting light after the meteor has gone. Upper atmosphere winds then stretch and twist that line into strange shapes. Those winds are moving at speeds that would count as hurricanes at ground level. So a persistent train is a windsock for a region nobody can reach. It sits too high for aircraft and too low for satellites to orbit. The second detail concerns everything you see on a night with no shower. There is a constant background of meteors arriving from no particular direction. Astronomers call those sporadics, and they run around 5 to 10 per hour. They come from the general debris population of the inner solar system. On any given night, most of what you see is sporadic background. Radar tells a much larger story than the human eye can. Meteor radar systems detect the ionized trails rather than the visible light. They register objects far too faint for anyone to see directly. What those systems reveal is a continuous rain rather than an occasional event. Something in the region of 100 tons of material arrives every day. Almost all of it is dust, and almost none of it is visible. Hold that figure in your head because it reframes the whole subject. 100 tons of extraterrestrial material lands on this planet daily. The atmosphere handles essentially all of it without any effect at ground level. One last thing about the light, because it explains a persistent argument. Some people report actually hearing meteors as they pass overhead, a faint hissing or crackling, arriving at the same moment as the light. For decades that was dismissed as imagination, and the reasoning seemed sound. Sound travels at roughly 1/3 of a kilometre per second. From 100 kilometres up, any real sound arrives minutes later. But the reports kept coming, from careful observers with no reason to invent them. The current explanation involves radio frequency energy rather than sound. Very bright meteors emit in the extremely low frequency radio band. That energy travels at the speed of light and arrives instantly. It then causes nearby objects to vibrate, including hair and eyeglasses. So the sound is generated at your end rather than at the meteor. Your own head is the loudspeaker, driven by a radio signal from overhead. I include that because it demonstrates something about this entire subject. A phenomenon reported for centuries was dismissed for sound physical reasons. The dismissal was wrong, because one variable had not been considered, which leaves exactly one question worth asking about any of it. What is doing the shedding, and how large is it? Two men found the answer in 1862 without understanding what they had. An Italian astronomer explained it 4 years later, and the argument then ran for a century. Part 3. The Italian who read a 2,000-year-old riddle. On the 16th of July, 1862, an amateur astronomer was observing from rural New York. His name was Louis Swift, and he found a faint smudge of light that night. It did not match anything in any catalogue he had access to. 3 nights later, on the 19th of July, a professional found the same object. Horace Parnell-Tuttle was working at Harvard College Observatory when he made the independent discovery. Neither man had any idea what he was actually looking at. What they had was a comet, and by 19th century standards it became a spectacular one. It brightened to roughly second magnitude, which matched the stars in the Big Dipper's handle. It then grew a tail spanning 25 to 30 degrees of sky. Let me anchor that number to something you can measure with your own hand. Your closed fist held at arm's length covers about 10 degrees of sky. So this object had a tail roughly 3 fists long hanging above the horizon. Anyone who walked outside at night could see it without any instrument. There is a detail about that discovery worth pausing on. Lewis Swift saw the object first on the 16th of July, but he was not at all certain what he had found. He assumed it was a comet already known and reported by others, so he did not immediately report it as a new discovery. Swift-Tuttle, 3 nights later, reported his sighting straight away. Under the naming conventions of the time, both men received credit. The object still carries both of their names to this day. Swift went on to discover more than a dozen further comets. He was working from an observatory built above a hardware store in Rochester. That is the kind of arrangement that produced a great deal of 19th century astronomy. I mention this because the pattern recurs throughout this entire story. An amateur sees something, hesitates over whether it matters, and the record nearly loses it. The same thing happens again in 1992 with far higher stakes. It became known as the Great Comet of 1862. Camille Flammarion was among the most widely read astronomers of the entire era. He later ranked it among the 10 finest comets of the 19th century. Then it left. Everyone went back to their lives, and the story should have ended. It did not end because of a man working in Milan 4 years afterwards. Giovanni Schiaparelli did something in 1866 that nobody had thought to attempt. He took the orbital path of a meteor shower and the orbital path of a comet. Then he laid one directly on top of the other and compared them. I need you to understand why that was such a strange thing to do. In 1866, nobody had any settled idea what meteors actually were. There were serious published proposals that they were an atmospheric phenomenon, some form of weather or an electrical discharge occurring in the upper air. The word meteor and the word meteorology share a root for precisely that reason. The connection to space was not obvious, and most people did not even suspect it. Schiaparelli computed the orbit of the August meteors that people had watched for centuries. Those meteors already had a name, and it came from the Christian calendar. They were called the Tears of St. Lawrence, after Lawrence of Rome. He was martyred on the 10th of August, in the year 258. That fell under the Emperor Valerian, and his feast day sits squarely on the peak. The records go back considerably further than the Christian tradition does. A Chinese chronicle from the year 36 describes the shower in plain language. It records more than 100 meteors flying in the morning sky. That is the earliest surviving written record of this specific shower. People have been watching this exact stream for at least 2,000 years. In 1835, the Belgian astronomer Adolphe Quetelet established it as a scientific annual event. He confirmed that the August meteors returned reliably, on schedule, every single year. Now hold both of those facts side by side for a moment. People had a 2,000-year observational record of an annual event. Nobody had any idea what was producing it, or where it came from. Schiaparelli found that the meteors travelled along a path nearly identical to the comets. Not merely similar, which would have been interesting but inconclusive, the same inclination, the same orientation in space, and the same orbital shape. His conclusion appeared in an exchange of letters with the Jesuit astronomer Angelo Secchi. He argued that the August meteors were physical pieces of the Great Comet of 1862. Debris shed along the comet's orbit as it travelled, left behind in a trail. The comet went round, dropped material, and once a year the Earth drove through it. That was the first time in history anyone linked a meteor shower to a parent body. It stands as one of the genuine hinge moments in the development of astronomy. It converted meteors from a weather phenomenon into a solar system phenomenon in one stroke. Within a very short time, Schiaparelli did the same for the November Leonids. He tied those to a different comet entirely, and the method was established. I want you to notice something specific about how he did it, because it recurs later. Schiaparelli never observed debris leaving the comet, and neither did anyone else at the time. He inferred the entire connection purely from the geometry of two computed orbits. He used mathematics to link a thing he could see to a thing he could not. That technique is the foundation of everything we now call planetary defense. Using orbital mathematics to reach conclusions about positions and times you cannot directly observe. Every statement about where a rock will be in a century rests on it. There is a second reason Schiaparelli's result mattered beyond the immediate finding. It gave astronomers a new way to detect objects they could not see. If a meteor stream exists, then a parent body existed at some point. The stream is evidence of the parent even when the parent is invisible. That logic runs in both directions, and it is still used today. Several parent bodies were found by first computing the stream orbit. The Alpha Capricornid parent was identified that way in 2005. The stream was known for over a century before the object was matched. 169P/NEAT had been catalogued as an asteroid. It turned out to be a mostly dead comet, and the stream proved it. So a meteor shower is a fossil of something that used to be active. Sometimes the animal that left the fossil is still walking around. Sometimes it disintegrated thousands of years ago and only the trail remains. It is also, as the next part of this story demonstrates, the thing that can fail badly, because within 20 years of Schiaparelli's work, astronomers tried to predict the comet's return. They had the orbit, they had the mathematics, and they had the confidence of the era. What happened next should have been a straightforward exercise in celestial mechanics. Instead, the comet did not come back when it was supposed to. Part 4. The comet that refused to arrive on time. The paper trail for this object is not clean, and the gaps in it matter enormously. In 1737, a Jesuit missionary named Ignatius Kegler was working in Beijing. On the 3rd of July that year, he recorded observations of a comet in the sky. The record went into an archive, and there it sat for well over a century. In 1902, an astronomer named William Lynn made a suggestion about that record. He proposed that Kegler's comet and the Great Comet of 1862 might match. Specifically, that they might be the same object returning after an absence. The interval between those two dates is about 125 years. That was in roughly the right neighbourhood, but it was not obviously correct. So the suggestion sat, unused and untested, for another 71 years. Do not skip past that detail, because it becomes the pattern of this entire story. In 1973, Brian Marsden took Lynn's suggestion seriously and did the arithmetic. Marsden worked at the Smithsonian Astrophysical Observatory in Cambridge, Massachusetts. He ran the Central Bureau for Astronomical Telegrams and the Minor Planet Center. For decades, essentially every comet and asteroid discovery on Earth crossed his desk. If you found something new in the sky, the procedure was simple. You reported it to Marsden, and Marsden decided what the object actually was. He linked the 1737 and 1862 apparitions into a single orbital solution. Then he propagated that solution forward to determine when the comet would return. His computed answer placed the next appearance in the early 1980s. The early 1980s arrived on schedule, and the comet did not. Astronomers looked for it, using far better instruments than anyone had in 1862. It was not there in 1981, and it was not there in 1982. It was not there in any of the years immediately following either. the most careful orbital mathematician of his generation had produced a prediction. The object itself had simply declined to honour that prediction. Sit with that for a moment, because there is a comfortable assumption buried underneath it. The assumption is that orbital mechanics is a fundamentally solved problem. Gravity is well understood, and the governing equations are more than 3 centuries old. You put in the positions and the velocities, you turn the handle, and you get the future. For a solid chunk of rock, that assumption is close enough to true. For a comet, that assumption fails, and it fails in a specific and unpredictable way. In 1981, the sky demonstrated that failure in the most public manner available. It demonstrated it by being empty on the night the mathematics said otherwise. The comet finally reappeared on the 26th of September, 1992. A Japanese observer named Tsuruhiko Kyuchi recovered it at magnitude 11.5. That is far too faint for the naked eye and required a serious instrument to find. Confirmations arrived shortly afterward from observers in Canada, the United States and Japan. It reached perihelion, its closest approach to the Sun, on the 12th of December that year. Its closest pass to Earth came earlier, on the 7th of November. That approach distance was about 177 million kilometres from this planet. To put that in context, the Sun sits about 150 million kilometres away, so the comet's closest approach was further from us than the Sun is. There is something worth noting about that 1992 recovery. Kyuchi found it using a large pair of binoculars from a mountain site. He was not operating a major observatory or a professional survey. He was an amateur who knew where to look and went looking. That matters because professionals had been searching for over a decade. The comet was faint and the predicted position was wrong. Sweeping a wide area of sky patiently is exactly what amateurs do well. Hold that pattern in mind because it appears twice more in this story. An amateur finds the object when the professional searchers cannot. An amateur later finds the records that save the entire calculation. The professional structure provides the mathematics and the institutional weight. The individuals working outside it repeatedly supply the missing piece. It reached about 5th magnitude at its brightest, which is faintly visible from a genuinely dark site. You needed to know exactly where to look, and you needed patience. It was nothing whatsoever like the spectacle of 1862. Now here is the number that everything from this point onward depends upon. Marsden's 1973 prediction had been wrong by 17 days. 17 days sounds like precision rather than failure, and I understand why. On an object with an orbital period exceeding a century, 17 days is a rounding error. It represents an error of roughly 1 part in 3,000 across the full orbit. By almost any standard of long-range prediction, that is an impressive result. Mark that number carefully, because it returns within 3 weeks and it changes meaning entirely. There is a historical precedent for the whole problem that is worth understanding. Edmund Halley computed the return of the comet that now bears his name. He published that prediction in 1705, and he did not live to see it. The comet returned in 1758, as he had said it would. That single success established that comets obey the same laws as planets. But look at what Halley actually had available for that calculation. He had well-documented observations from 1531, 1607, and 1682. 3 apparitions spread across 151 years of records. He recognised that all 3 described one object on one orbit. That is exactly the same situation Marsden faced with Swift-Tuttle in 1973. 3 apparitions again, spread across 255 years. The same method applied to the same class of problem. Halley's own prediction proved accurate too within about a month. Marsden's prediction missed by 17 days on the arrival date. Both men were doing careful work with the tools available. and both were fighting the same hidden variable in the equations. Halley did not know the variable existed, and Marsden could not measure it. That variable is the reason Comet prediction resisted solution for 3 centuries. Because Marsden now had something he had never possessed before this recovery. He had fresh, precise, modern positional measurements on an object he had already failed to predict. Combined with 1737 and 1862, he had 3 separate apparitions. He did what any orbital dynamicist does when handed new data on an old problem. He refitted the orbit, and then he propagated it forward to find the next return. The result of that calculation was published on the 15th of October, 1992. It contained one sentence that would follow this object for the next 34 years. But before I can show you that sentence, I have to show you the object. Because the sentence only becomes frightening when you know what it is describing. Part 5. 26 kilometers, and the gap that is 1/3 of the way to the moon. Let me put the actual measurements on the table, because everything downstream depends on them. I would rather you had the numbers in front of you than take my conclusions. The object is catalogued as 109p/Swift-Tuttle. The number simply marks its place in the sequence of comets confirmed to return periodically. The letter P stands for periodic, meaning we have seen it come back. Its orbital period is about 133 years by the standard published solution. That solution gives 133.28 years for a single circuit. Because of a resonance effect I will explain shortly, the long-term average differs. Averaged across many orbits, the period sits closer to 130.5 years. The orbit itself is extremely elongated, far more than any planetary orbit. Its eccentricity is 0.9632 on a scale I should define. 0 on that scale is a perfect circle, and 1 is a parabola that never returns. So this object sits right at the edge of remaining bound to the Sun at all. At its closest approach to the Sun, it reaches 0.9595 astronomical units. 1 astronomical unit is the average Earth to Sun distance, roughly 150 million kilometers. Read that figure again, slowly, and compare it to where you are standing. The Earth orbits at 1.0 astronomical units by definition of the unit. That comet, at its closest approach to the Sun, is inside the Earth's orbit. At the far end of its path, it travels out to 51.2 astronomical units. That is well past Neptune, out toward the region of space where Pluto lives. Let me make that orbital shape concrete with a comparison you can hold. Picture a very long and very thin ellipse rather than a circle. The Sun sits near one end of it rather than in the middle. For roughly 120 of its 133 years, the comet is inert. It is beyond the orbit of Jupiter, frozen, dark, and producing nothing. It is functionally invisible to every instrument that we currently possess. The entire visible life of this object happens in a few short years. Everything we know about it was learned in those brief windows, 1737, 1862, and 1992. 3 separate windows, each one lasting a matter of months. That is the total observational basis for everything asserted about it. So the shape of this object's life is a very long fall and a very fast whip. It falls inward from the outer solar system across more than a century. It rounds the Sun from inside our orbital distance at enormous speed. Then it begins a 100-year climb back out into the dark. The orbital inclination is 113.45 degrees, and that figure carries real weight. Any inclination above 90 degrees means the object orbits backwards relative to the planets. It is retrograde, which means in plain terms that it runs against traffic. That single property is responsible for most of what follows, and I will return to it. Now the size. which is the figure everyone quotes and almost nobody contextualizes. The effective diameter is about 26 kilometers across the nucleus. That value comes from the standard compilation of measured cometary nuclei. There is real uncertainty attached to it, and I will not hide that. Some analyses put the radius above 11 kilometers as a hard floor. Certain estimates from the 1990s ranged as high as 30 kilometers. So call it 26 kilometers, with meaningful error bars in both directions. 26 kilometers is an abstraction until you set it beside something familiar. The asteroid Apophis was the most famous impact scare of the 2000s. It will pass closer to Earth than our geostationary satellites in 2029. Let me slow down for this comparison, because the ratios matter enormously. Its mean diameter is about 340 meters across the whole body. The long axis of Apophis measures at least 450 meters. The asteroid Bennu is an object we visited with a spacecraft and sampled directly. Laser altimetry measured it at 490.06 meters across. The stated uncertainty on that figure is plus or minus 16 centimeters. That level of precision tells you what becomes possible with a spacecraft parked alongside something. The asteroid 2024 YR4 triggered the first formal international asteroid warning ever issued. That notification went out in January of 2025, and the object is small. It measures somewhere between 40 and 90 meters across its longest dimension. The nucleus of Swift-Tuttle measures 26,000 meters across. It is roughly 50 times the diameter of Bennu, which we treated as a major mission target. In volume terms, and therefore roughly in mass terms, that ratio becomes enormous. The factor lands somewhere in the region of 100,000. The nucleus rotates roughly once every 2.8 days, which is about 67 hours. Assume a radius of 13.5 kilometers for the calculation. Assume also the low densities typical of comet nuclei, around 0.6 grams per cubic centimeter. The resulting mass works out on the order of 10,000 trillion kilograms. I want to flag something honestly about that figure before you carry it forward. The density there is assumed rather than measured, because nobody has visited this object. Treat the mass as an order of magnitude statement rather than a precise value. During the 1992 apparition, observers at the Pic de Midi Observatory watched it closely. That facility sits high in the French Pyrenees using a 1.05 meter telescope. What they imaged coming off the nucleus were spiral jets of material. Dust was leaving at around 300 meters per second through a cone 20 degrees wide. Radio observations found hydrogen cyanide streaming outward at 1.1 kilometers per second. Remember the word jets, because it becomes the central mechanism of this entire story. Remember also that those jets were spiral, meaning they rotated along with the nucleus. They swept around in space exactly like a garden sprinkler on a lawn. Now the number that the entire risk assessment turns on. It is called the minimum orbit intersection distance, shortened in the field to MOID. It is the single most important quantity in any discussion of impact hazard. MOID is not how close an object comes to Earth on any given pass. It measures how close the two orbital paths come to each other as fixed curves. Picture two racetracks laid out across a landscape, crossing over one another. The MOID is the gap between the tarmac of one track and the other. It is measured at the point where those two surfaces come nearest together. It tells you nothing whatsoever about whether two cars are there simultaneously. For Swift-Tuttle, the Earth MOID is about 0.001 astronomical units. Converted into kilometers, that lands somewhere between 130 and 150,000. The Moon orbits this planet at a distance of 384,000 kilometers, so the orbital path of a 26-kilometer body passes remarkably close to ours. The gap between the two tracks is about 1/3 of the Earth-Moon distance. That is among the smallest Moid values known for any large object in the solar system. That single figure is what gets quoted, stripped of context, in every alarming article ever written. So let me be precise about what a small Moid does and does not mean. A small Moid is a necessary condition for any impact ever occurring. It is nowhere close to being a sufficient condition on its own. Two racetracks can cross with a gap of 1 meter between them. If the cars are never at the crossing point together, nothing ever happens. What a small Moid genuinely tells you is that this object requires permanent monitoring. The geometry does not rule out a collision the way it does for most objects. It is an open invitation to keep watching, indefinitely, forever. What it is not, under any reading, is a prediction of anything. There is one more orbital property worth explaining, because it does real work. I mentioned a resonance earlier and promised to return to it. Swift-Tuttle sits in what is called a 1:11 mean motion resonance with Jupiter. In plain terms, it completes one orbit for every 11 Jupiter completes. That relationship is not a coincidence, and it is not fragile. It is a stable configuration that the system has settled into. Stay with me here, because this is the property that keeps the orbit stable. What a resonance does is control when the two bodies actually meet. Because the ratio is fixed, the geometry of each encounter repeats predictably. The Comet and Jupiter never find themselves in the worst possible arrangement. Jupiter's gravity, therefore, does not accumulate into a destabilizing kick over time. That resonance is one of the reasons the orbit has held for so long. It is also part of why the 2,000-year arc fits so cleanly. A chaotic orbit would not have produced observations matching across 20 centuries. Swift-Tuttle was the first comet found in a retrograde orbit inside a resonance. That combination is rare, and it is part of what makes the object unusual. But there is a second number attached to this object, and that one is different. The Moid has a reassuring interpretation available if you understand the geometry properly. The next figure has no reassuring interpretation of any kind. Part 6. The number that has no comforting version. Earlier I asked you to carry a relationship forward with you. Kinetic energy scales with the square of velocity, not with velocity itself. Here is where I hand that relationship back to you. The overwhelming majority of objects that could strike Earth are asteroids. They inhabit the same region of the solar system that we occupy. They orbit in the same direction we do, and their paths align broadly with ours. Because of that shared geometry, an impact is essentially a catching-up maneuver. One object overtakes the other or gets overtaken at a modest relative speed. Typical impact velocities for asteroids land somewhere around 17 to 20 kilometers per second. Swift-Tuttle is retrograde, and that changes the arithmetic completely. It is not travelling with the traffic in any sense. It is coming directly the other way around the Sun. When it crosses Earth's orbital plane, the two bodies move almost straight at each other. The relative velocity in that geometry is about 60 kilometers per second. An actual impact velocity would come in around 61 kilometers per second. Watch what happens to the arithmetic now, because it is not a small adjustment. Take 20 kilometers per second as an ordinary asteroid impact for comparison. 60 kilometers per second is 3 times that ordinary figure. 3 squared is 9, and energy follows the square of velocity. So 1 kilogram of Swift-Tuttle arrives carrying 9 times the energy of ordinary material. Not 9% more energy, and not a modest increase. 9 times, kilogram for kilogram, purely from the direction it travels. And you are not comparing a kilogram against a kilogram in any real scenario. You are comparing an object roughly twice the diameter of the Chicxulub impactor. That object is also moving at roughly 3 times the ordinary encounter speed. Let me walk through the calculation the way it has been done in the literature. Take a nucleus radius of 13.5 kilometers as the input. take a density of 0.6 grams per cubic centimetre, which is deliberately conservative, take an impact velocity of 61 kilometers per second at arrival, then run the standard kinetic energy calculation on those inputs. The result comes out on the order of 2.75 billion megatons of TNT equivalent. That is roughly 27 times the energy released by the Chicxulub impact. The astrophysicist and science writer Ethan Siegel put that figure into more visceral terms. Writing for a general audience, he described it as more than 1 billion megatons of energy. He characterized that as the equivalent of 20 million hydrogen bombs detonating at once. I want to be scrupulous here, because that number gets stripped of its caveats constantly. The 27 times figure is a popular science calculation rather than a peer-reviewed study. It applies a well-understood formula, and I see no reason to think the arithmetic wrong, but it rests on an assumed density and an assumed radius for the nucleus. If the real density would double the assumption, the energy figure would double as well. So treat it as a statement about order of magnitude and nothing finer. The order of magnitude is what matters, and the order of magnitude is stark. This would not be an extinction event comparable to the one that killed the dinosaurs. It would be substantially worse than that event, by a considerable margin. I want to make that comparison concrete rather than leaving it as a ratio. The Chicxulub impact occurred roughly 66 million years ago in the Yucatan. The resulting crater measures between 180 and 200 kilometers across. The impact deposited a thin global layer of iridium in the sediment record. That layer is found on every continent, and it marks a boundary in the rock. Below that layer, the fossil record describes one version of this planet. Above that layer, the fossil record describes something else entirely. Something like 3/4 of all species on Earth did not survive. The tsunami generated by that impact has been estimated at extraordinary scale. Modelling work puts it at something like 30,000 times the 2004 Indian Ocean event. But here is the part that killed most of what died. The impact itself was survivable for anything not in the immediate region. What was not survivable was the aftermath that followed over months. Vaporized rock thrown into space re-entered the atmosphere across the whole planet. That re-entry heated the upper air enough to broil exposed surfaces. Then the dust and sulfate aerosols blocked sunlight for an extended period. Photosynthesis largely stopped, and the food chain collapsed from the bottom upward. So the crater was not the mechanism of the extinction at all. The crater was the trigger, and the atmosphere was the weapon. Bring back the two crossing racetracks for a moment. A collision at the crossing point is not the whole story. What matters is everything that happens after the two cars meet. Now scale all of that by a factor near 27. That is the arithmetic of a 26-kilometer nucleus at 60 kilometers per second. Now let me tell you how one of the people who understood this best described it. Gerrit Verschuur is a radio astronomer with a long career in the field. In 1997, Oxford University Press published his book on the impact hazard. Writing about this specific comet, he used a phrase that has followed it ever since. He called it the single most dangerous object known to humanity. Not the most dangerous comet, and not the most dangerous object known to astronomy. Known to humanity, published by an academic press, by a working scientist. I could leave that quotation sitting there, and a great deal of coverage does. But you deserve to understand why a serious scientist would use language that strong. It is not hyperbole, and it is not marketing for a book jacket. It follows directly from 4 properties this single object holds simultaneously. The first property is sheer size, at 26 kilometers across the nucleus. That is large enough that atmospheric effects become completely irrelevant to the outcome. An object that size arrives essentially intact, regardless of what the air does. The second property is velocity, at 60 kilometers per second from the retrograde orbit. The squared relationship then does the remainder of the work by itself. The third property is the orbital geometry, with a moid near 1/1000th of an astronomical unit. The two paths very nearly touch, as the racetrack comparison showed. The fourth property is recurrence, and I think it is the one people miss. This object comes back every 133 years or so, indefinitely. It will keep doing that for as long as it holds together as a body. This is not a single pass carrying a single probability figure. It is a repeated draw with identical geometry on a timescale outlasting civilizations. Any one of those four properties alone would be entirely unremarkable. There are plenty of large bodies in the solar system, and plenty of retrograde ones. There are many low-moid objects, though most of them are small. There are thousands of catalogued periodic comets making regular returns. All four properties combined in one body is what produced that sentence in that book. Set that against Apophis for a moment, because the contrast is instructive. Apophis will pass Earth on the 13th of April, 2029. Its closest approach brings it inside the ring of geostationary satellites. That is roughly 32,000 kilometers above the surface. It will be visible to the naked eye from parts of Europe and Africa. Around 2 billion people will be in a position to watch it, and it is completely harmless, because we measured it thoroughly. Radar observations pinned that orbit down to extraordinary levels of precision. The impact possibilities for 2029, 2036 and 2068 were all eliminated. Apophis is the model case for how this is supposed to work. Detection, then tracking, then refinement, and finally a definitive answer. It took roughly 17 years of work to reach that answer. 17 years of continuous work on an object 340 meters across. Now scale that effort to something 26 kilometers across arriving unannounced. And now I have to tell you something that will feel like a contradiction. Swift-Tuttle is not on any risk list maintained by any agency anywhere. It does not appear on Sentry, which is the automated impact monitoring system. Sentry is operated by the Center for Near-Earth Object Studies at the Jet Propulsion Laboratory. The Comet carries no non-zero impact probability for any foreseeable approach. Donald Yeoman spent his career at that laboratory doing exactly this kind of orbital work. He put the current position about as plainly as anyone could. He said that we have to be clear that it is not going to happen. So both statements are true simultaneously, and that should bother you. A serious scientist called it the most dangerous object known to humanity. The agency responsible for tracking impact threats does not list it as one. That is not a contradiction, and resolving it is the whole point of this story. The resolution happened across roughly 8 weeks in the autumn of 1992. What it reveals is not reassuring in the way you would expect, because the reason we know this object is safe has almost nothing to do with telescopes. Part 7. The sentence that contained a date. On the 15th of October 1992, Marsden published his result. It appeared as International Astronomical Union Circular number 5636. I want you to understand the document itself before you hear its contents. Let me explain what a circular actually was, because the format explains everything afterwards. Circulars were the nervous system of observational astronomy for most of the 20th century. They were short, dense, and telegraphic in style, with no wasted language. They carried orbital elements, discovery announcements, and brightness estimates for new objects. They went out to observatories worldwide as the field's mechanism for informing itself. They were not press releases, and they were not written for any public audience. They were technical notes passed from professionals directly to other professionals. They used a compressed style where every single word carried substantial weight. That compression happened precisely because there were so few words available. Circular 5636 carried the full orbital solution. The perihelion date was given as the 12th of December, 1992. Eccentricity was listed as 0.96359. Perihelion distance came in at 0.95812 astronomical units. Inclination was recorded as 113.430 degrees. The semi-major axis was 26.31666 astronomical units. Orbital period was given as 135 years. Then it contained a single sentence of commentary from Marsden himself. He wrote that extrapolating forward gave the next perihelion date directly. That date was the 11th of July in the year 2126. He noted that the problem of computing the non-gravitational forces must introduce some uncertainty. Then he wrote the clause that made this object famous for 34 years. A change by plus 15 days could cause the comet to hit the Earth. The date he attached to that possibility was the 14th of August, 2126. That is the sentence, written in flat technical register in a specialist document. It came from the most respected orbital mathematician working anywhere in the world. Now bring back the number I asked you to mark earlier in this story. Marsden's 1973 prediction had been wrong by 17 days. The margin he was now describing between a safe pass and an impact was 15. Let me say that again slowly, because it is the crux of the entire episode. The man who wrote that sentence had made an error on this exact object. That error occurred within his own working memory, and it was 17 days. The error that would put the comet into the Earth was 15 days. His documented track record of failure was larger than the margin separating us from catastrophe. He was not being dramatic when he wrote that clause. He was being rigorous, which is a different thing entirely. He had a documented 17-day miss on this specific body. He had no reliable method for modelling the forces that had caused it. The arithmetic said 15 days of drift in one direction produced a collision. Any honest scientist looking at that situation would write the possibility down. Marsden wrote it down in the appropriate technical register and moved on. And then it escaped the technical literature and entered the world. The press coverage through the end of 1992 was predictably enormous. It continued through much of 1993 across every major outlet. Doomsday Comet, the comet that could end the world, and similar constructions. The detail driving almost all of it was the size comparison to Chicxulub. Reporters had spent the previous decade learning about the impact that killed the dinosaurs. Now here was an object roughly twice as wide as that one, and this one, unlike that one, came with a specific calendar date attached. 2126 is not a comfortable distance in the future. It is not some abstract point at the heat death of the universe. It sits roughly 134 years ahead of the present moment. There are people alive today whose great-great-grandchildren would reach middle age by then. I want to make a point about the media dynamic here. It recurs in every single case of this kind, without exception. Marsden's sentence was conditional in its structure, and that structure carried its meaning. It said that a 15-day shift in one particular direction made this possible. Everything depended on that opening word, and on the direction specified. Strip that conditional away, and you are left with a bare prediction. Keep the conditional intact, and you have an honest acknowledgement of a known unknown. The conditional clause did not survive contact with the headline, and the cost of losing it was not confined to 1992. The cost is that 34 years later, the phrase most dangerous object known to humanity persists. It remains attached to this comet in the popular imagination, floating free. It is disconnected from the reasoning that produced it, and from the work that resolved it. I need you to feel the weight of what Marsden was actually admitting in that sentence. He was saying that his own calculation contained a dominant error term. That error term came from a physical phenomenon he could not model. He could not model it because the necessary input data did not exist. It did not exist because it cannot be measured from Earth for an object like this. That admission is far more interesting than the date, and far more relevant today. There is one more element of the 1992 coverage worth examining. It concerns what the public was actually told about probability. Marsden never assigned any probability at all to that impact scenario. He could not have done so, and that was precisely his point. A probability requires a distribution of possible outcomes with known weights. He did not have the distribution, because he could not model the driving force. So what he published was a bound rather than an estimate. He said the outcome was not excluded by the available data. That is a fundamentally different statement from saying it was likely. The distinction matters enormously, and it recurs constantly in this field. Not excluded is the weakest possible statement a scientist can make. It means only that the evidence does not rule something out. Coverage routinely converts that into a claim about actual likelihood. Watch for it the next time an object appears in the news. If nobody is quoting a probability figure, there is usually a reason. So the question that determined whether that date meant anything is a physical one. What are these non-gravitational forces, and why can nobody compute them? The answer turns out to be one of the strangest facts about comets. It is also the reason this object was ever frightening in the first place. Part 8. The rocket engine bolted to a mountain of ice. Everything you have ever been taught about orbital prediction assumes one thing quietly. It assumes that the object being tracked is entirely passive. It assumes the object is dead weight, moving only in response to gravity. Know every gravitational influence acting on it, and you can compute its position forever. For asteroids, that assumption holds well enough to build a defense posture on. There are subtle non-gravitational effects involving thermal radiation pressure over long periods. Those effects are small, they are understood, and they can be modelled. A comet is not passive in any sense of that word. A comet is a machine that switches itself on when it gets warm. Here is the mechanism behind it, built up one piece at a time. A comet nucleus is a mixture of ice, dust and rock bound loosely together. The ices include water, carbon dioxide, carbon monoxide, and a range of complex compounds. Out beyond Jupiter, the whole body is frozen solid and completely inert. As it falls inward toward the sun, the instant sunlight intensifies enormously. The surface ices do not melt into liquid at those pressures. They sublimate instead, passing directly from solid straight into gas. That gas expands violently away from the surface, dragging dust along with it, and every gram of gas leaving in one direction pushes the nucleus the other way. What I have just described to you is a rocket, not a metaphor for a rocket, and not a loose analogy. It is a functioning rocket engine running on solar power mounted to a mountain of ice. Now consider what makes this genuinely uncontrollable rather than merely complicated. If gas came off uniformly in every direction, all the pushes would cancel out, nothing measurable would happen to the orbit, and the problem would vanish. But Comet's surfaces are patchy rather than uniform, and that ruins everything. An insulating blanket of dust and stay cold beneath it. Other regions crack open and expose fresh ice directly to sunlight. That fresh ice then blows off in a concentrated directional jet of gas. Bring back what the Pictomidi observers imaged in 1992. Spiral jets, with dust leaving at 300 meters per second. The cone of that outflow measured about 20 degrees across. None of that describes a diffuse haze surrounding the nucleus evenly. What they photographed was a directed exhaust nozzle firing into open space, and the nucleus rotates once every 2.8 days beneath that nozzle. So the jet sweeps around continuously, exactly like a garden sprinkler on a lawn. The direction of thrust changes constantly as the body turns underneath it. Whether the net effect across a whole perihelion passage speeds the comet up depends on several things. It depends on where the active regions happen to sit on the surface. It depends on how the rotation axis is oriented relative to the Sun. It depends on when during the approach each individual vent switches on. It depends on whether any of them get buried by fallback debris partway through. None of those variables can be observed from Earth for this particular object. It is only bright enough to study for a few months every century and a third. So the honest position is uncomfortable but simple to state. We can measure the effect after the fact by observing how early or late the comet arrives. We cannot predict that effect in advance from first principles. Let me give you the historical scale of these deviations, because the numbers are concrete. Comet Encke returns to perihelion every 3.3 years reliably. It arrives roughly 1/10 of a day early on each successive return. It has done so consistently since the effect was first identified after its 1822 return. Halley's Comet shows non-gravitational deviations reaching up to about 4 days. 4 days on a comet with historical records stretching back across millennia. Now go back to Marsden's claws with those figures in your hand. He needed 15 days of drift to produce an impact. Halley routinely produces 4 days of it without anyone being surprised. Marsden had personally been wrong by 17 days on this exact object. And Swift-Tuttle is far larger than Halley in every dimension. A larger body offers more surface area for something unexpected to crack open. Here is the comparison that I think captures the problem best. Imagine predicting where a car will be in 100 years' time. You know the road surface, the gradient and the friction involved. There is no driver in the vehicle at any point. That is asteroid dynamics, and it is hard but closed. Now put a small rocket motor on the roof of that same car, then mount that motor on a turntable which rotates continuously. Arrange for the motor to fire whenever the sun happens to be shining. Then allow yourself to see the car for 1 month every century. That is comet dynamics, and no amount of computing power resolves it. The problem is not arithmetic, and it never was arithmetic. The problem is that the necessary input data does not exist to be entered. We are not uncertain because our mathematics is weak, or our computers are slow. We are uncertain because the object we are tracking is actively steering itself. There is direct observational evidence for all of this, and it is recent. Rosetta watched a comet nucleus continuously for 2 full years. What it saw was not a steady process at all. Activity switched on and off as different regions rotated into sunlight. Jets appeared, ran for hours, and then shut down entirely. New jets opened elsewhere as the illumination geometry slowly changed. Hold on to this next detail, because it demolishes any hope of prediction. The comet also had seasons, which is not something that people expect. Its rotation axis was tilted relative to its orbital plane. One hemisphere received far more heating than the other during the approach. Activity then migrated across the surface as those seasons progressed, and material fell back onto the nucleus rather than escaping entirely. Some regions were buried under debris shed from elsewhere on the body. Those buried regions then stopped producing any gas at all. Every one of those behaviours changes the thrust vector on the nucleus. None of those behaviours can be predicted before they happen. All of them were observed happening on a real comet in real time. So when Marsden wrote that he could not model the non-gravitational forces, he was not hedging. He was describing a physical system that we have since watched behave exactly as feared. So in October of 1992, the situation was precisely this. An object 26 kilometers across, moving at 60 kilometers per second, amoyed roughly 1/3 of the way to the Moon. An orbit that could not be predicted better than about a fortnight. A prediction horizon of 134 years to the next return, and a date printed in a circular distributed to every observatory on Earth. The question is how any of that got resolved within 8 weeks. The answer has essentially nothing to do with astronomy, as it existed in 1992. Part 9. The amateur who found 2,000-year-old paper. The way you reduce uncertainty in an orbit is by extending the observation arc. That principle is simple, and it governs everything in this field. Observe an object for 1 week, and your century-long prediction is worthless. Observe it for a year, and the prediction improves but remains poor. Observe it across multiple complete orbits, and something fundamentally different becomes possible. You can then measure the accumulated effect of the non-gravitational forces directly. You do that by seeing how far the object has drifted from pure gravity. Each additional return hands you another independent measurement of that drift. In October of 1992, the arc for Swift-Tuttle was thin. It consisted of exactly 3 apparitions across the entire historical record: 1737, 1862, and 1992 itself. That is 255 years of coverage and 3 separate data points. 3 points is not enough for a problem of this kind. Stay with this, because the arithmetic here is the whole problem. 3 points on a curve being perturbed by an unmodelable force gives almost no leverage. You cannot separate the size of the drift from the errors in the measurements. What was needed was more returns, and there was no obvious way to get them. This is a 133-year object, and you cannot travel backwards in time. Except that somebody found a way to do exactly that. Gary Kronk was not a professional astronomer, and held no academic position. He was an amateur, a cataloguer, and a man with unusual persistence. He spent years assembling comprehensive historical records of every cometary observation he could locate. Not new observations from modern instruments, but old ones from archives. Chinese dynastic records, Korean and Japanese chronicles, and European monastic annals. Astronomy performed by people who had never seen a telescope. Those people nonetheless watched the sky with an attention that modern societies have largely abandoned, and crucially, they wrote down what they saw with dates attached to it. Kronk went looking for comets appearing at roughly correct intervals before 1737. He needed them in the right part of the sky, with the right apparent motion. He eventually found 2 candidates that fit every one of those requirements. One came from the year 69 before the Common Era, the other came from the year 188 of the Common Era. He took both of those ancient records directly to Brian Marsden. Marsden ran the 2 ancient observations through his orbital solution, and both of them fit the computed historical positions of the comet. Not approximately, and not in a way requiring generous interpretation. They fit well enough to be entered into the official record permanently. Based on the surviving descriptions, that 188 apparition was genuinely brilliant. It appears to have reached around magnitude 0.1 at its brightest. That would place it among the brightest objects in the entire night sky. Now look at what those 2 records did to the observation arc. Before Kronk, the arc was 255 years and 3 documented apparitions. After Kronk, the arc stretched to approximately 2,064 years. The number of documented returns roughly tripled in a single afternoon. None of that counts as an incremental improvement to a calculation. That is a transformation of the entire problem being solved. With returns spanning 2 millennia, the drift becomes directly measurable. You are no longer estimating the size of an unknown error term. You are observing that error term, integrated across 2,000 years of orbits. When Marsden finally performed that calculation, the answer changed everything at once. The drift proved far smaller and far more consistent than the worst case had allowed. He retracted the warning in December of 1992. It went out as Circular 5670. Roughly 8 weeks separated the publication of the date from its withdrawal. Stop here for a moment, because I want the shape of this to land properly. The most serious impact scare of the 20th century involved the largest known repeat visitor. That scare was resolved by 2 observations made by scribes in ancient China. One of them was recorded roughly 2,060 years before the calculation. It was written down in an era when the sky was understood in entirely different terms. Somebody thought a broom star overhead was worth noting, and they noted it. Those records sat in archives for 2 millennia, serving no purpose their authors imagined. Then, in 1992, they suddenly became load-bearing. They were the difference between an object with a date and an object without one. I want to say something about the people who made those observations, because the modern instinct is to treat them as lucky amateurs. Chinese astronomical record-keeping was a continuous state function for over 2,000 years. Court astronomers held official positions with defined responsibilities and defined penalties. Their job was to record anything unusual appearing in the sky. Comets, novae, eclipses, sunspots and meteor showers all went into the record. They wrote down the date, the position among the constellations, and the apparent motion. Frequently they recorded the length of the tail and the changing brightness. They did this because unusual sky events were understood as politically meaningful. A broom star overhead was read as a comment on the legitimacy of a dynasty. That belief was mistaken about causation and entirely correct about the value of recording. The result is the longest continuous observational record produced by any civilization. Modern astronomers use it routinely for things its authors never anticipated. Supernova remnants have been dated using Chinese records of guest stars. The Crab Nebula is tied to an observation recorded in the year 1054. So Kronk was not lucky in the way that word implies. He was drawing on a 2,000-year dataset that already existed. What he supplied was the connection between that dataset and a live calculation. There are 2 ways to read that outcome, and most coverage takes only the comfortable one. The comfortable reading is that the scientific process worked exactly as designed. Uncertainty was identified honestly, more data was located, and the calculation improved. The apparent threat then evaporated entirely under the weight of better information. That reading is entirely correct, and I do not want to undercut it. Take it seriously before I hand you the other one. The uncomfortable reading is the one I keep returning to. We did not have that data in October of 1992. It existed, in the sense that it sat in a library somewhere. It did not exist in the sense that anybody had connected it to this object. The resolution arrived from information that had gone unused for 2,000 years. It was found by an amateur, essentially because he was doing thorough work nobody commissioned. If Gary Kronk had chosen a different hobby, the arc stays at 255 years. The date then remains in that circular, uncontested and completely unresolved. The honest scientific position remains that an impact cannot be ruled out. Nothing about the comet itself changed across those 8 weeks. Its orbit in December was identical to its orbit in September. The mass was the same, the velocity was the same, the geometry was the same. The only thing that changed was what we happen to know. Our safety on that question was never a property of the solar system. It was a property of one man's sustained personal attention. That distinction is going to become the spine of everything that follows. Because if being safe is a property of attention rather than of physics, one question follows. What exactly are we not paying attention to right now? Part 10. What the word safe is actually hiding. When an agency describes an object as safe, that word does very specific work. It is not doing the work most people assume it is doing. Let me give you the current figures for Swift-Tuttle from the modern solution. Then I will explain what those figures guarantee and what they do not. The next perihelion falls on the 12th of July in the year 2126. The close approach to Earth follows shortly afterward on the 5th of August. The approach distance is 0.153 astronomical units. That converts to about 22.9 million kilometers from this planet. Measured in miles, that distance is roughly 14.2 million. Relative velocity during that pass will be about 58.3 kilometers per second. For scale, that approach distance is about 60 times the Earth-Moon separation. Comfortable by any operational standard anyone uses in this field, and it will be genuinely spectacular for whoever is alive to watch it. The projected brightness sits around magnitude 0.7 at best. That would place it among the brightest stars visible in the sky. Anyone alive in 2126 walks outside and sees it unaided. It will hang there, visible without equipment, for weeks at a time. The 3 sigma uncertainty on that approach distance is about 10,000 kilometers. Sit with that figure because it demonstrates exactly what Kronk's 2 records purchased. 10,000 kilometers of uncertainty on a position 134 years ahead. The Earth itself measures nearly 13,000 kilometers across its diameter, so the uncertainty in that prediction is smaller than the width of this planet. In 1992, the uncertainty was measured in 15-day chunks of arrival time. Now it is measured as a distance smaller than the Earth itself. That is what a 2,000-year observation arc actually buys you. The published record then extends considerably further out into the future. On the 15th of September, in the year 3044, another approach occurs. The distance is roughly 1.6 million kilometers, or about 1 million miles. That is around 4 times the Earth-Moon distance from us, substantially closer than 2126, but still not a threat. Then comes the year 4479. Published work by John Chambers, and separately by Yao, Yeomans and Wiseman, addresses that encounter. Their analyses from the mid-1990s give an approach distance range. It falls somewhere around 0.03 to 0.05 astronomical units. The associated impact probability sits on the order of 1 in a million. After that encounter, the per-orbit probability settles near 2 in 100 million. So here is what the word safe actually means in this context. Impact has been excluded for approximately the next 2,000 years. Beyond that horizon, the numbers are not zero at all. They are simply extremely small, and they become increasingly uncertain over time. That growing uncertainty has a name, and the name is chaos. I want to introduce that word carefully because it gets misused constantly. Chaos in orbital mechanics does not mean random or unpredictable in principle. It means tiny differences in starting conditions grow exponentially as time passes. 2 nearly identical starting positions diverge slowly, then faster, then completely. Every close pass by a planet amplifies that divergence further. For a comet, every perihelion passage adds another unpredictable kick from the jets. So there is a prediction horizon, and it is a hard limit. Inside that horizon, prediction genuinely works, and the numbers mean something. Outside it, you can only discuss probability distributions, and eventually, not even those. For Swift-Tuttle, that horizon sits somewhere around the 5th millennium. Now let me show you how these numbers behave in practice. There is a recent case where the entire process ran in public. In December of 2024, a survey telescope in Rio Hurtado, Chile, detected something. It was part of the Atlas system, and the object became 2024 YR4, between 40 and 90 meters across, which is small by the standards of extinction. It is city damaging rather than civilization ending, but very much not nothing. By the 29th of January, 2025, it triggered a formal notification. That was the first in the history of the International Asteroid Warning Network. It climbed to level 3 on the Torino scale of impact hazard. No object had reached that level since Apophis, decades earlier. The impact probability for the 22nd of December, 2032, then rose. The European Space Agency put it at 2.8% on the 18th of February. The Centre for Near-Earth Object Studies put it around 3.1%. That works out to roughly 1 chance in 32. I want you to hear that figure as it deserves to be heard. Imagine a flight you were booked on carried a 1 in 32 failure chance. You would not board that aircraft, and neither would I. Nobody would board that aircraft, and nobody would consider the decision difficult. That is the correct emotional response to a 3% impact probability. Then, observations from the Very Large Telescope in Chile arrived on the 19th of February. The impact probability halved almost immediately once that new data arrived. Further work by a team at the University of Helsinki refined it further. The figure collapsed to something in the range of 0.1%. The object dropped to Torino 0 and left the risk list. Then a genuinely strange thing happened as the Earth risk vanished. A moon impact possibility emerged from the same refined orbital data. It peaked in early April at around 3.8% according to NASA. The Helsinki group put it near 4% using James Webb Space Telescope observations. Those were combined with continued ground-based tracking of the object. What matters in that sequence is not the specific asteroid involved. What matters here is the shape of the process itself. The calculated probability went up substantially before it went down. That is not a failure of the system, and understanding why is essential. When you first detect something, the uncertainty region is enormous. It forms a vast elongated cloud of possible future positions. The Earth occupies a tiny fraction of that cloud, so the probability is tiny. As data accumulates, the cloud shrinks around the true path. If Earth remains inside the shrinking cloud, it occupies a larger fraction of it, so the calculated probability rises, sometimes dramatically, as precision improves. It keeps rising until the cloud shrinks small enough to miss Earth entirely. At that point, the probability drops to 0 almost instantly. So a rising impact probability is the normal signature of an object about to be cleared. That holds true in the overwhelming majority of observed cases. The phrase overwhelming majority is doing enormous work in that sentence. There is no way in advance to know which case you are looking at. There is one more thing about the word safe that I want to isolate. It concerns what happens to an object after it leaves the risk list. When the probability drops to 0, the coverage stops immediately. The object remains in the catalogue, and its position continues to be computed. But the public attention that briefly surrounded it disappears entirely. That is the correct outcome in the overwhelming majority of cases. The object genuinely is safe, and there is nothing further to discuss. But notice what the process trains people to expect over time. Every object that generates a headline is eventually cleared entirely. The pattern repeats until being cleared feels like the natural ending. It begins to feel like the headline itself was the error. That is a reasonable inference from the data available to a viewer. It is also the exact belief that would make the eventual exception invisible. That is the process that ran for Swift-Tuttle across 8 weeks in 1992. It ran to completion, and the final answer was 0. There is one more comparison I want to make before moving on. It concerns how the 2024 YR4 case ended. When the Earth risk vanished, the Moon risk appeared in its place, and the reaction to that was revealing about how we process these things. A 4% chance of a lunar impact generated relatively little coverage. The same probability aimed at Earth had dominated news cycles for weeks. That difference is entirely rational, and I want to be clear about that. A lunar impact harms nobody, and it would be scientifically valuable. It would be the first time we watched a known object strike the Moon. But notice what the public attention was actually tracking there. It was tracking the threat to us, rather than the science. The moment the threat moved, the attention moved with it, which is the correct response for a population, and the wrong one for a system. The objects that matter most are the ones nobody is watching yet. Which brings me to the part where the comet stops being the problem. Part 11. Every object with a name is already safe. I have spent a long time building the case that this one body is exceptional. Now I am going to take that case apart, because the historical record points elsewhere. It does so with a consistency that I find genuinely difficult to look away from. Here is the reframing, and I want you to test it against everything I have said. Every object I have named so far shares one specific property. Swift-Tuttle shares that property, and so does the asteroid Apophis. Bennu shares it too, and so does 2024 YR4. Each of them has a designation, a computed orbit, and a database entry. And every single one of them is, as a direct consequence, safe, not safe, because of anything intrinsic to the objects themselves. Safe because somebody found them and started measuring their positions. Once an object enters the catalogue with a decent observation arc, prediction becomes possible. We then compute its position for decades or centuries into the future. If it were going to hit us, we would know years or decades in advance. The catalogue is not a list of dangers waiting to arrive. The catalogue is a list of things that have already been cleared. So the obvious question follows on immediately from that observation. Where does the actual damage in the historical record come from? Let me give you 3 specific dates, each with a hard number attached. The first is the 30th of June, 1908. An object entered the atmosphere over the Podkamennaya-Tunguska River in Siberia. It measured somewhere in the region of 50 to 60 meters across. It did not reach the ground, and it detonated in the air instead. Energy estimates in the literature vary considerably, and I will give you the range. They run from a few megatons at the low end to 50 at the high end. Figures around 10 to 15 megatons are the ones most commonly cited. The blast flattened roughly 2,150 square kilometers of forest. That is around 80 million trees, knocked flat in a radial pattern. Every trunk pointed away from a single point in the sky. 2,150 square kilometers is larger than the land area of Greater London. Nobody saw that object coming, and in 1898 nobody could have. No instrument anywhere on Earth was capable of detecting it in advance. The second date is the 15th of February, 2013. An object roughly 20 meters across entered the atmosphere over Chelyabinsk in Russia. It released somewhere between 440 and 500 kilotons of energy. Around 1,500 people were injured in that event. 112 of them were hurt badly enough to require hospitalization. The overwhelming majority of injuries came from flying glass rather than the object. Windows across the city blew inward when the shockwave finally arrived. Roughly 7,200 buildings sustained damage across 6 separate cities. And here is the part of Chelyabinsk that actually matters for this discussion. That object was not detected at any point before it arrived. It was not detected late, and it was not detected poorly. It was not detected at all, and the warning time was precisely 0. The reason for that is worth understanding, because it is not a funding failure. It is not a technology failure either, and that distinction matters. Chelyabinsk approached the Earth from the direction of the Sun. Optical telescopes work by detecting reflected sunlight against a dark background sky. An object arriving out of the sunward sky is drowned in glare. The problem was not that anybody looked in the right place and missed it. From the ground, in that geometry, the object was simply invisible. That particular blind spot has not been closed in the years since. It is still open above your head, exactly as it was in 2013. The third date is the 25th of July, 2019. An asteroid now designated 2019 OK passed this planet closely. It measured roughly 100 meters across, which is Tunguska scale and then some. Keep the size of that object in your mind for a moment. Its closest approach was about 0.19 lunar distances from Earth. Measured in kilometers, that comes out to roughly 70,000. 70,000 kilometers is well inside the Moon's orbit around us. It is not far outside the ring of geostationary communication satellites. That object was detected only days before the pass occurred. Not decades of warning, not years of warning, and not even months. The total warning available to anyone was measured in single days. An object large enough to destroy a metropolitan area passed inside the Moon's orbit. We found it on the way in, with essentially no time to do anything. Take those three events together and look at what they share. Tunguska arrived in 1908 with precisely zero warning given. Chelyabinsk arrived in 2013 with precisely zero warning given. 2019 OK gave days of warning, with the approach already underway. None of those three objects was in any catalogue when it arrived. There are two further cases worth adding, because they are physically documented. Not inferred from treefall patterns or reconstructed from damage reports. On the 12th of February 1947, an iron meteorite fell in eastern Siberia. It came down in the Sikhote-Alin Mountains in broad daylight. Witnesses described a fireball brighter than the sun crossing the sky. Roughly 23,000 kilograms of iron reached the ground intact. It produced more than 100 separate craters on impact. The largest of those craters measured about 26 meters across. That is the largest observed meteorite fall in recorded history. It happened within living memory, and pieces of it sit in museums. The second case is smaller, and it involves one person directly. On the 30th of November 1954, a meteorite struck a house in Alabama. The town was Sylacauga, and a woman named Ann Hodges was inside. The object weighed about 3.9 kilograms when recovered. It came through the roof, struck a radio cabinet, and hit her while she rested. She sustained a large bruise across her hip and side. That remains the only well-documented case of a person being struck. One confirmed instance in the entire written record of humanity. I include those two because they anchor this in physical objects. Not statistics, and not models, but iron sitting in a display case in a museum. Put your hand on that idea for a second before I continue. That is the pattern the historical record makes impossible to ignore. The public conversation about impact risk concerns named objects almost exclusively. Named objects can be written about because they have numbers and approach dates. They have probability figures that can be updated, and they generate headlines. But the entire damage record of the modern era comes from unnamed objects. Every injury, every flattened forest, and every shattered window came from something uncatalogued. There is a detail about Tunguska that says something about our attention. Nobody scientifically investigated that impact site for 19 full years. The event happened in June of 1908 in remote Siberia. Reports reached the outside world, and seismographs across Europe recorded the shock. Atmospheric dust produced unusually bright nights across Europe for weeks afterward, and then essentially nothing happened at all for almost 2 decades. A Russian mineralogist named Leonid Kulik finally reached the site in 1927. He expected to find a crater and a large iron meteorite. He found neither because the object had detonated in the air. What he found instead was 80 million trees flattened in a radial pattern. At the centre, trees remained standing, but were completely stripped of branches. The blast had come from directly overhead rather than from the side. 19 years passed between the largest impact event of the modern era and its investigation. That gap opened not because anyone decided it was unimportant, because it happened somewhere remote and other things seemed more pressing. I want to add one more event, because it removes any argument that this is theoretical. Between the 16th and the 22nd of July, 1994, Jupiter was struck. 21 separate fragments of a comet hit the planet across 6 days. The comet was designated Shoemaker-Levy 9, and it had already come apart. Jupiter's tides had torn it into pieces during an earlier close pass. The pieces returned in a line, one after another, on the same trajectory. The fragment designated G was the largest object in that group. Its impact released energy estimated at around 6 million megatons. For scale, that is on the order of 600 times the entire global nuclear arsenal. That comparison uses the arsenal at its Cold War peak. The plume from that single fragment rose about 3,000 kilometers above the cloud tops. The dark scar it left behind measured around 12,000 kilometers across. The Earth measures 12,742 kilometers across. Hold those two figures next to each other for a moment. A single fragment of a single comet left a bruise the size of this planet. It was watched live, by telescopes on the ground and by a spacecraft in flight. That happened in the summer of 1994 within living memory. It was the first time human beings directly observed a collision between two solar system bodies. So the question of whether large impacts still occur is closed. They occur, and we have watched one happen in high resolution. The only remaining variable is which body happens to be in the way. Which brings me back to the objects nobody has named yet, because for asteroids there is at least a survey program working the problem. For comets arriving from the outer solar system, the situation is entirely different, and the numbers on how much warning we would actually receive are worse than you expect. Part 12. 55 days, and a planet that was simply in the way. For a catalogued near-Earth asteroid, warning time is measured in decades. We know where Apophis will be in 2029 and in 2036. That lead time is the entire reason deflection is possible at all. A tiny velocity change applied 20 years out becomes an enormous position change. For a long-period comet arriving from the outer solar system, the picture inverts. Warning time is measured in months, and occasionally in a year or two. These objects spend almost their entire existence far from the sun. Out there they are dark, cold, and completely undetectable by any instrument we have. They become visible only once they are already inside Jupiter's orbit. That is the point where the surface ices begin to sublimate seriously. By the time you can see one at all, it is most of the way here. I do not want to leave that as an abstraction, because the record has specific cases, and the numbers in those cases are considerably worse than most people expect. On the 30th of January, 1996, a Japanese amateur found a comet. His name was Yuji Hyakutake, and he was using a large pair of binoculars. What he found was faint, and nobody could see anything remarkable in it yet. On the 25th of March, 1996, that comet passed the Earth. Its closest approach was about 0.1 astronomical units from this planet. That works out to roughly 15 million kilometers of separation. It became one of the brightest and most spectacular objects of the decade. Its ion tail stretched across a substantial fraction of the visible night sky. Count the interval between those two dates along with me. The 30th of January to the 25th of March. That is 55 days from first detection to closest approach. 55 days for a large comet passing inside a tenth of the Earth-Sun distance. I want to be completely clear that nothing was missed in that case. There was no failure of any survey, and nobody was negligent. The object simply was not detectable earlier than it was found. It was too far out and too cold to produce enough coma to see. Now, that particular comet was never going to strike us. Its orbital geometry was not aimed anywhere near this planet. But the detection timeline is the detection timeline regardless of geometry. It does not care whether an object is aimed at us or not. If something on that same approach profile had been aimed at Earth, the arithmetic holds. The total warning available would have been under 2 months. 2 months is not enough time to launch anything meaningful. It is barely enough time to convene the relevant people for a meeting. Here is the second case, and I find this one considerably harder to dismiss. It involves a planet that was actually in the path. On the 3rd of January 2013, Robert McNaught discovered a comet. He was observing from Siding Spring Observatory in Australia at the time. The object received the designation C2013A1. Informally, everyone called it Siding Spring after the observatory that found it. On the 19th of October 2014, that comet passed Mars. The approach distance was approximately 140,000 kilometers from the planet. 140,000 kilometers is about 1/3 of the Earth-Moon distance. For a planetary encounter with a comet, that is extraordinarily close. It was close enough that mission controllers took direct protective action. Every operational spacecraft in Mars orbit was repositioned before the passage. Controllers moved them to put the planet between themselves and the incoming dust. The relative velocity was high enough to make that necessary. At those speeds, a single millimeter-sized grain would destroy a satellite outright. Total warning time from discovery to that encounter was about 21 months. 21 months is considerably better than 55 days. It is still nowhere near enough time to be useful. Every deflection concept requires the velocity change to be applied years in advance. What you buy with a tiny nudge is a large position change over a long flight. Apply that same nudge 21 months out, and the object arrives in roughly the same place. Now notice something specific about the nature of that Mars encounter. Mars received no warning in any meaningful operational sense at all. Mars was simply there, in its orbit, and the comet went past. Had the alignment differed by a small fraction, the outcome changes completely. An object roughly half a kilometer across would have struck a planet. And the entire human response would have consisted of watching it happen. We would have moved some satellites and recorded the result in high resolution. That is our actual capability against this class of object today. We can observe, model, protect hardware, and document exactly what occurs. Beyond those 4 things, the list of available options is empty. There is one more piece of context worth adding, and it cuts the other way. I want to include it because honesty requires the counterweight. Comet Hale-Bopp was discovered on the 23rd of July, 1995. It was picked up while still more than 7 astronomical units from the Sun. That gave roughly 20 months of lead time before its perihelion passage. Hale-Bopp was found that early for one specific reason. It was exceptionally large, and it was already active at that enormous distance. So there is a general rule buried in that comparison. The larger the comet, the earlier you are likely to see it coming. That rule is genuinely reassuring, and I do not want to undersell it. It is the reason we can be reasonably confident nothing enormous is inbound unnoticed right now. But reasonably confident is the correct phrasing, and every word in it matters. The confidence degrades quickly as the size of the object falls, and the size at which that confidence degrades is a problem. It sits well above the size that would end a civilization. There is one more warning time case worth putting on the record. It happened in 2023, and almost nobody noticed it. A small asteroid was detected by a Hungarian observer named Kristin Snecki. He found it roughly 2 hours before it entered the atmosphere. It came down over the English Channel near the French coast. Fragments of that object were later recovered on the ground in Normandy. 2 hours of warning on an object roughly 1 metre across. That is a success story, and it demonstrates real capability. Predicting the impact point of a small object hours ahead is genuinely difficult. But hold the number in your hand and consider what it means. Our current best case for a small incoming object is a couple of hours. That is enough time to tell people to stay away from windows. It is not enough time to do anything else at all. Scale the object up and the detection distance improves considerably. Scale it up far enough and the warning becomes years. Somewhere between those two extremes sits every object that could ruin a region. Now put every piece of that together, because this is the summary. So the arithmetic of the worst realistic case comes out like this. An object you have never catalogued, arriving on a first passage from the outer solar system. It arrives on retrograde geometry at something near 60 kilometers per second. Detection happens somewhere between 6 and 18 months before arrival, facing deflection methods that all require years of lead time to function. That is not a scenario with a technical solution available, not with the hardware and the launch capacity that exist right now. There is one more comparison that puts the warning problem in perspective. It concerns how much of the sky we actually watch. Survey telescopes cover an enormous area, but they do not cover everything continuously. A given patch of sky gets revisited every few nights at best. Objects moving quickly can cross a gap between two observations. Objects approaching from the sunward direction are not observed at all. There is also the southern hemisphere problem, which is straightforward. Historically, most survey capacity has been located in the northern hemisphere. Coverage of the southern skies has been thinner for decades. 2019 OK was found from Brazil, days before its pass. None of that is a scandal, and none of it is negligence. Telescopes cost money, and sky coverage is a resource allocation problem. But the practical consequence is a system with structural gaps in it, and an object only has to fit through one of those gaps once. Which raises an obvious objection, and I want to address it directly. The objection is that we have already deflected an asteroid successfully. We did it in public with a spacecraft, and it worked better than predicted. So why does none of that capability help us here? The answer is a matter of arithmetic, and the arithmetic is brutal. Part 13. We moved an asteroid, and it changed nothing about this. On the 26th of September 2022, a spacecraft flew into a moon. The moon was called Dimorphos, and it orbits a larger asteroid named Didymos. The spacecraft was called DART, and it massed about 570 kilograms. It struck at roughly 6 kilometers per second, and Dimorphos is about 170 meters across. The success criterion had been set in advance and published openly. Mission planners needed a change in the orbital period of at least 73 seconds. The initial result was announced on the 11th of October, 2022. The measured period change was about 32 minutes, with an uncertainty near 2 minutes. The refined analysis came later and was led by Steve Naidu. Naidu works at the Jet Propulsion Laboratory, and the study appeared in the Planetary Science Journal. His team settled the final figure at 33 minutes and 15 seconds. The stated accuracy on that measurement was within about 1.5 seconds. 33 minutes against a target of 73 seconds. They beat the benchmark by a factor of more than 25. I want you to understand why they beat it so comprehensively, because the reason matters. Pure momentum transfer would have produced only about 7 minutes of change. That is the figure if the spacecraft simply stops dead inside the asteroid. The additional 26 minutes came from ejecta thrown off the surface. the impact blew a plume of material away from Dimorphos entirely. That material leaving in the opposite direction acted as additional thrust on the body. The multiplier describing that extra push is known as beta. For this impact, beta came out somewhere between 2.2 and 4.9. The European Space Agency launched a follow-up mission in October of 2024. The spacecraft is called Hera, and it arrives at that system around the end of December. Its task is to measure the mass of Dimorphos precisely. Doing so will pin down the value of beta properly for future planning. That is real capability, demonstrated in public against a real target. It works, and the people who built it deserve the credit. There is a detail from the aftermath that I find genuinely striking. Follow-up observations showed that DART did not simply push Dimorphos aside. The impact appears to have reshaped the entire body itself. The object appears to have been deformed by the impact itself. A loosely bound rubble pile does not behave like a solid billiard ball. It absorbs the energy by rearranging its own internal structure. Material was thrown off, and the remaining body settled into a different shape. That is why the ejector contributed 4 times more than the spacecraft did, and it is why Hera's measurements matter so much for future planning. If you do not know the internal structure, you cannot predict the outcome. You would be guessing at the most important number in the calculation. Notice how similar that problem is to the Comet jets. In both cases, the uncertainty comes from internal structure we cannot observe. In both cases, you only learn the answer by arriving and measuring. Now let me show you why none of it scales to the problem we have been discussing. DART changed the velocity of a 170-meter rubble pile. The change was a fraction of a millimeter per second. That was sufficient, because the target was small and the deflection had years to accumulate. A tiny velocity change becomes a large position change given enough flight time. Swift-Tuttle is 26 kilometers across, with a mass near 10,000 trillion kilograms. That is something in the region of 100,000 times the mass of Dimorphos. Quite possibly considerably more than that, given the uncertainties in density. Momentum is conserved, and that conservation law is not negotiable. To impart the same velocity change to something 100,000 times heavier, you need proportional momentum, not 100,000 times the budget, which would merely be expensive. 100,000 times the momentum, delivered to a specific point at a specific time. Delivered, additionally, to a target closing at 60 kilometers per second. And there is a further problem that is worse than the mass ratio. At 60 kilometers per second closing speed, the interception geometry is close to head-on. Every interceptor must either launch into a retrograde trajectory itself or accept that combined velocity. The engineering difficulty involved is not an incremental step up from DART. It is a categorical difference in the nature of the problem. Then there is the gravity tractor concept, which people often propose as the elegant solution. You park a heavy spacecraft alongside an object and let mutual gravity pull it. Over years, that gentle tug tows the object onto a different path. It is a genuinely clever idea for small bodies with long lead times. Against a mass of that scale, the achievable displacement is negligible. Then there is the nuclear option, which people reach for as the universal answer. Set aside the political and legal questions entirely for a moment. Consider only the physics involved in a standoff nuclear detonation. It works by ablating one side of the object with radiation. That blows material off the surface, and the escaping material provides thrust. It is the same principle DART used, delivered by a different mechanism. The efficiency still depends entirely on the mass you are trying to push. Against 10,000 trillion kilograms, you would need a delivery campaign resembling nothing ever built, and you would need that campaign operating years in advance. Bring back the roof-mounted rocket motor for a moment. because it applies here too. You are trying to intercept a car with an engine you cannot switch off. That car is steering itself unpredictably the whole time you approach. You get one attempt, and you must aim years before arrival. That is the deflection problem for a comet in a single image. Now, I want to be fair, because the picture is genuinely improving in real ways. The Planetary Defense Coordination Office has grown enormously over 2 decades. It ran on something like $4 million a year in the early 2000s. It now runs at roughly $200 million a year. About 40 million of that goes to ground-based observation programs. That is a real program with real hardware and real people. And a significant new instrument is coming, with a specific launch window. It is called NEO-Surveyor, and it is an infrared space telescope. The instrument is a 50-centimeter aperture with 2 heat-sensing bands. Amy Mainzer leads the mission, and it will operate from the first Sun-Earth Lagrange point. Launch is currently set for no earlier than September of 2027. There is a commitment to June of 2028, at the very latest. The mission is a 5-year survey with a defined completeness goal. It aims to find at least 2/3 of the undiscovered near-Earth objects. That target applies to everything above 140 meters across. The choice of infrared matters enormously, and I want to explain why. Infrared detects heat rather than reflected sunlight from an object's surface. A dark object that is nearly invisible optically glows brightly in the infrared. Albedo stops being the limiting factor in what you can find, and crucially, operating from space allows the instrument to look nearer the sun. Ground-based telescopes cannot do that, because the atmosphere scatters sunlight across the whole sky. That is the Chelyabinsk blind spot, being addressed directly and deliberately. The gap that let a 20-meter object arrive with zero warning is being closed, but look carefully at the specification of what that survey covers. Objects 140 meters and larger in the near-Earth population. That is the asteroid problem, and it is being solved competently. A long-period comet on a first passage is outside that design case entirely. It is not there to be found until the moment it arrives. We are building an excellent solution to the problem we can characterize. The problem we cannot characterize remains exactly where it has always been. There is one further obstacle that has nothing to do with physics. It concerns who would actually make the decision to act. There is an international structure for this, and it is worth knowing about. The International Asteroid Warning Network handles detection and notification between countries. A separate body called the Space Mission Planning Advisory Group handles response planning. Both were established under United Nations auspices in 2014. Those 2 bodies coordinate, advise, and issue formal recommendations to members. Neither of them commands anything, and neither controls a launch vehicle. So a real deflection campaign would require several spacefaring nations to agree. They would need to agree on the threat assessment first, then on the method, then on the cost, then on the timeline, and they would need to do all of that while the object approached. 2024 YR4 is the closest thing to a live test we have. It reached Torino 3, and the network functioned exactly as designed. Notifications went out, telescope time was allocated, and the orbit was refined. That worked because the required action was observation rather than intervention. Nobody had to agree to launch anything at all anywhere, and that raises a question people ask constantly in one form or another. I want to answer this one properly rather than waving it away. Is any of this actually getting worse than it was before? Is the solar system becoming more dangerous than it used to be? The honest answer is more interesting than either position people usually take. Part 14. The sky is not getting more dangerous. We are getting better at looking. The question comes in several forms, and they all point the same direction. whether there is more activity now than there used to be, whether the rising number of detections means a rising number of objects. The short answer is no, and the reason is almost entirely about instruments. Here is the mechanism sitting behind that apparent increase in danger. In 1990, the number of known near-Earth objects sat in the hundreds. Today that same catalogue holds well over 30,000 separate entries. That is a genuinely enormous increase across a single human lifetime. Plot it on a graph, and the curve looks alarming, but nothing new arrived in the solar system during that period. What changed was our ability to see what was already present. We built survey telescopes that scan the entire visible sky repeatedly and automatically. We wrote software that compares each night's images against the previous nights. Anything that moved between frames gets flagged for follow-up observation. The population was always out there, and we simply acquired the ability to detect it. You can prove that internally from the data itself, which I find satisfying. If new objects were genuinely arriving, one thing would stay constant. The size distribution of newly discovered objects would remain roughly stable over time. What actually happens is that the average size of new discoveries falls every year. That is the precise signature of a survey working downward through a fixed population. We found the biggest objects first, because they are the easiest to detect. We have been working steadily downward through the size range ever since, so the growth of the catalogue measures our attention rather than our danger. There is a second way to test that claim, and it uses the moon. The lunar surface preserves a complete impact record with no erosion. No weather removes craters there, and no plate tectonics recycles the surface. Counting craters of different sizes gives you an impact rate over time. Radiometric dating of returned samples anchors that count to actual dates. What that analysis shows is a rate that has been broadly stable. It has been stable for something like the last 3 billion years. I want that point to land clearly before I move on. There was a period of far heavier bombardment much earlier than that. But it ended long before anything complex lived on this planet, so the flux has not increased in any measurable way. The moon has been keeping the records, and the records are consistent. Now, having said that plainly, I want to complicate it slightly. There is one respect in which the last decade genuinely changed the picture. That change has nothing to do with rates of arrival at all. We discovered that objects come here from outside the solar system entirely. Until 2017, that was a purely theoretical category of object. Astronomers assumed such things existed, but had never confirmed one. Now it is an observed category, and each detection has been stranger than the last. The first was found in October of 2017 and named Oumuamua. It was small, extremely elongated, and showed no visible coma at all. It also accelerated slightly in a way gravity alone did not explain. Debate about that acceleration continues in the scientific literature today. The second arrived in 2019 and was called Borisov. That one behaved like an ordinary comet in almost every respect. It had a coma, it had a tail, and its chemistry was broadly familiar. The only unusual thing about it was where it came from. The third was detected in 2025 and designated 3I/Atlas. It reached perihelion in October of that year and is now outbound. 3 confirmed interstellar visitors in 8 years, after none in all of history. That is not because the rate of arrival suddenly changed. It is because the survey capability finally crossed a threshold. And there is a thread running through this story that connects directly to that. I flagged it early, and now I want to pick it back up. The southern delta aquarids are one of the 3 streams currently crossing our path. Their suspected parent is the Comet 96P/Mach-holes. And Mach-holes is chemically wrong in a way that is difficult to explain. It is severely depleted in cyanogen and in carbon chain molecules. Essentially every other comet ever measured carries those compounds in reasonable abundance. Comets that formed within the same disk of material should share a broad chemistry. This one does not, and the discrepancy is not marginal. That has produced a serious published hypothesis about where the object came from. Either it formed in a very different region of the solar system, or it did not form within this solar system at all, captured at some point in the deep past, and now running a 5.3-year orbit. I am not telling you that hypothesis is established, because it is not. It is a proposal with real supporting evidence and real published opposition. But notice the shape of what I just described to you. An object that has been in the inner solar system for a very long time, catalogued, numbered, tracked, and producing an annual meteor shower every July. People photograph its debris every summer without thinking about it. And we are not certain where the parent body originally came from. That is the actual state of our knowledge in this field. It is not a wall of ignorance, and I want to be accurate about that. It is a very detailed map with unlabeled regions scattered across it. While we are discussing what is happening right now, there is one other item worth noting. It illustrates the same principle from an entirely different direction. The Sun is currently active, and it has been for the past several days. As of the end of July, the solar disk carried several complex sunspot regions. Their magnetic configurations were complex enough to produce significant flares. On the 30th of July, a long-duration flare erupted from one of them. That region was rotating toward the western limb at the time. The eruption was accompanied by a filament eruption and a partial halo-coronal mass ejection. Radio signatures were recorded at 853 kilometers per second. A second signature came in at 1,681 kilometers per second. The proton flux crossed the threshold for a minor radiation storm. That crossing occurred at 1845 Universal Time on the same day. Forecasters issued a watch for geomagnetic storm conditions on the 2nd of August. That watch covers the arrival of the cloud launched on the 30th. And here is the detail that connects it back to everything else. Earlier in July, a storm arrived 2 full levels stronger than forecast. Consider what that means about the state of the art. The people making that forecast were observing an object 8 light minutes away. They observe it continuously, in multiple wavelengths, with a fleet of dedicated spacecraft. And that event still surprised those forecasters by a substantial margin. The reason is a single variable they cannot measure in advance. The orientation of the magnetic field inside the cloud determines the severity. That orientation cannot be measured until the cloud is roughly 15 minutes out. This is the same structural problem as the comet jets. It is not a failure of mathematics or of computing power. It is a variable that is physically unmeasurable until it is too late to act. So if there is a pattern here, it is not that space grows more dangerous. Across completely unrelated domains, the limiting factor turns out to be identical. There is always one term in the equation you cannot reach in advance. Everything downstream of that term is therefore an estimate rather than a fact. Before I leave this question, there is one figure worth stating plainly. It concerns how much of the dangerous population we have actually found. For the largest objects, those above 1 kilometer across, the survey is nearly complete. Somewhere above 90% of that population has been catalogued. Those are the civilization-ending objects, and we have essentially found them. For objects above 140 meters, the picture is very different. That is the size that destroys a region rather than a planet. Completeness there sits somewhere around 40% by most estimates. NeoSurveyor exists specifically to push that figure toward 2/3. For objects in the Tunguska range, around 50 meters, completeness is poor. The great majority of that population has never been observed. There are estimated to be hundreds of thousands of them, so the honest summary of our position is layered rather than simple. The objects that would end everything are largely accounted for. The objects that would end a city mostly are not. Which brings me back to a specific date and to 3 cycles arriving together. Part 15. 1 night, 3 cycles, and a shadow crossing Iceland. Now let me bring the timelines together, because they intersect on a specific date. That date is 11 nights from now, and the arrangement is worth examining. The first of those timelines belongs to the debris itself. Every grain in the Perseid stream left that nucleus at some point in the past. Most of them departed a very long time ago indeed. Each has been travelling on its own independent orbit ever since. Those grains have no propulsion and no capacity to change course. They are simply moving along the paths they were handed, and every year in early August, the Earth drives through the sheet of them. Follow both of these clocks with me, because they are about to meet. That clock has been running on the same schedule since before written history. The Chinese record from the year 36 describes the shower already in progress. The tradition of the Tears of St. Lawrence attaches to a death in 258. Adolphe Quetelet established it as a scientific annual event in 1835. Schiaparelli finally explained the cause of it in 1866. So people watched this exact stream for 2,000 years without knowing its source. The second of those timelines belongs to the parent comet itself. It is out there right now, somewhere beyond the orbit of Neptune. It sits in the dark, frozen solid, and completely inert. It reached perihelion in December of 1992 and has been climbing since. It will keep climbing outward for decades yet before it turns. Then it begins the long fall back toward the Sun. It reaches perihelion again on the 12th of July, 2126. That clock has a period of 133 years per cycle. It has been running for a very long time already. And it has an end state we cannot compute past roughly the 5th millennium. 2 clocks, one fast and one slow, driven by the same object. The 2 of them intersect above your head every August without fail, and on the 12th of August, 2026, a third thing happens. It has no causal connection to either of the first 2. The Perseid peak this year falls on a new moon. Illumination is 0%, so the sky is as dark as it gets. Rates should be the best observed since 2018 for that reason. That same new moon also produces a total solar eclipse. On the 12th of August, 2026, the moon's shadow crosses the Arctic. That shadow then passes over Greenland, Iceland, and northern Spain. A corner of Portugal catches the edge of the track as well. Greatest eclipse occurs at about 1747 Universal Time. That point sits roughly 45 kilometers off the west coast of Iceland. Duration at greatest eclipse is 2 minutes and 18 seconds. The umbral band reaches up to about 294 kilometers wide. It is the first total solar eclipse to touch mainland Europe since 1999. That previous event fell on the 11th of August, 27 years ago. For Spain specifically, the wait has been considerably longer than that. The last one there fell on the 30th of August, 1905. That is a gap of 121 years between events. Give this a moment to settle before I go any further. So consider what arrives in one sky on one single date. The darkest possible conditions for the densest annual meteor stream we receive. That stream is produced by the largest object known to make repeated close passes, and on the same day, the moon covers the sun over Europe. None of those 3 things causes any of the others. The eclipse and the dark meteor conditions share one common cause, which is the new moon. The comet has nothing whatsoever to do with either of them, but all 3 are happening in the same sky on the same date, and I think there is something worth noticing in that arrangement. It is not mystical, and it is not evidence of any pattern. The solar system runs on an enormous number of independent cycles. They all have different lengths, and they all run simultaneously and indefinitely. Every so often, several of them align by pure arithmetic, which is also the exact mechanism by which the dangerous alignments occur: an orbit, and another orbit, and a moment in time. None of them are related to each other in any way. All three arrive at the same point at the same moment. That is what an impact is when you strip away the drama. It is nothing more than a coincidence of cycles, one of which happens to be ours. Now let me be practical about the next few weeks, because you can act on this. The Perseids build through the first week and a half of August. Rates climb gradually at first, then sharply in the final nights. The maximum falls on the night of the 12th into the 13th. Calculated peak is around 14:53 Universal Time on the 13th. That timing favours observers in Asia and Eastern Europe for the exact maximum. The peak is broad enough that the whole Northern Hemisphere gets a good night. Under genuinely dark skies, expect somewhere between 50 and 80 meteors per hour. The theoretical figure of 100 assumes the radiant directly overhead. It also assumes a perfect sky, which nobody anywhere actually has. From a suburban location with streetlights, expect 15 to 25 per hour. That is still roughly 1 meteor every 3 minutes across the night. I would take that arrangement gladly and without any hesitation. The radiance sits in the constellation Perseus, and its position is fixed. Write this down if you intend to go out and watch. Its right ascension is about 3 hours and 13 minutes. Declination is about 58 degrees north of the celestial equator. It rises in the northeast during the late evening and climbs through the night. That means the rates improve steadily toward the early hours of morning. The best observing window generally falls between midnight and dawn. You do not need any equipment whatsoever to watch this properly. A telescope is actively counterproductive here, and I want to explain why. It narrows your field of view to a fraction of a degree. The meteors themselves can appear anywhere across the entire visible sky. Lie back, look up, and give your eyes 20 minutes to adapt properly. Do not look at a phone screen during that period. A single glance at a bright screen resets the adaptation completely. Now the branching scenarios, because there are 2 of them. The data currently supports one over the other quite strongly. The first scenario is the ordinary one, and it is the likely one. The Earth passes through the well-characterized portion of the stream. Rates run roughly as forecast, and the shower behaves as it has for decades. That is what the models say, and it is what I expect to happen. The second scenario is an outburst, and it is far less likely. The stream is not uniform in density, and that is the key point. It carries internal structure that persists over very long periods. Individual dust trails, each shed at a particular perihelion passage, remain distinct. They have not yet spread out and merged into the general background. Jupiter's gravity herds these trails around, bunching some and dispersing others. There is a known feature within the stream called the Perseid filament. It is associated with material shed around the 1862 passage. When the Earth crosses a filament, rates do not increase by a modest percentage. Instead, they multiply, sometimes by a very large factor indeed. In the years immediately around the 1992 perihelion, this happened repeatedly. From about 1989 through 1995, observed rates climbed sharply. Some years reached as high as 500 meteors per hour. The 1993 event ran roughly 3 to 5 times normal. Historical outbursts are also recorded in 1861 and 1863. Those were the years immediately following the comet's discovery in perihelion. That timing is not coincidental, and it reveals the underlying pattern. Outbursts cluster around the comet's returns, when fresh material remains concentrated. As decades pass, the fresh trails spread and the enhancements fade. We are currently 34 years past the last perihelion. We are roughly 100 years from the next one. So we sit firmly in the quiet portion of that cycle. The ordinary scenario is heavily favoured by every model available. But I want to be honest that outburst prediction is not a solved problem. Models have missed outbursts that subsequently occurred with no warning at all. Models have also forecast events that then failed to materialise at all. The enhancement in 2016 was anticipated correctly in advance. Several other enhancements across the decades were not anticipated at all. So the most honest answer the data allows is a qualified one. Expect an ordinary but excellent Perseid year, made unusually good by the moon. The improvement comes from the darkness rather than from the stream itself. Do not expect an outburst, because the cycle argues strongly against one. But do not be astonished by one either, and here is why. The resolution of our maps of that debris is not fine enough to promise you. Beyond September, the schedule stretches out across generations rather than weeks. The comet climbs outward, and the stream keeps arriving every August. In 2126, the object returns and dominates the sky for a season. There is a piece of the observing advice I want to add, because it changes results. It concerns where you point your attention across the sky. Do not stare directly at the radiant point in Perseus. That is the intuitive move, and it is the wrong one. Meteors appearing near the radiant travel almost straight toward you. Their apparent trails are therefore very short and easy to miss. The longest and most spectacular trails appear well away from the radiant. Look about 40 to 60 degrees off it in any direction. Roughly halfway up the sky is the general working rule. That geometry gives you the longest apparent path across your field of view. Bring back the garden sprinkler comparison for just one moment. Stand directly in front of the nozzle and you see very little movement. Stand off to the side and the arc becomes obvious. The same principle governs how a meteor shower presents itself to you. The radiant is a perspective effect rather than a physical location. Those particles are all travelling on parallel paths through space. They only appear to diverge from a point because of your viewing angle. It is exactly the same illusion as railway tracks converging toward a horizon. The tracks are genuinely parallel, and your eye insists otherwise. Nobody hearing these words will live to see that return, and that fact, more than any other in this story, is the actual problem. Part 16. 4 dangers, and the one that nobody can put a name to. There is a mismatch running underneath this entire subject, and I want to name it. I think it explains more about our behaviour than any of the physics does. The comet has an orbital period of 133 years. A human working life runs to about 40 years at most. An institutional memory, in practice, runs shorter than either of those. Consider what that mismatch actually means operationally, rather than abstractly. Everyone who observed the 1862 apparition was dead before 1992. Not one person alive in 1992 had seen this object before. Every observation made that year was a first observation for everybody involved. The same will be true when it returns in 2126. Nobody alive at that return will have witnessed the previous pass. The continuity of knowledge about that object exists entirely in records. It does not exist in anybody's memory or anybody's professional instinct. That is a fragile way to carry information across centuries, and we have excellent evidence of exactly how it fails. Marsden's 1973 prediction was built on the 1737 Beijing observation. That record had sat unrecognised for 165 years. William Lind suggested the link in 1902, and then it sat again. Another 71 years passed before Marsden actually used it. Kronk's two ancient records had been sitting for 2,000 years. In both cases, the information existed continuously the entire time. In both cases, the gap between existence and usefulness was measured in centuries. The bottleneck in both cases was never the data itself. The bottleneck was somebody finally connecting it to a live problem. I raise this because the same structural problem applies to the real hazard, and to see why, you need to understand how the damage would actually arrive. The reason a large impact would be catastrophic is not primarily the crater. For anything short of a Chicxulub scale event, the crater is not the story. Most of the damage comes from what happens to the systems people depend on. Those systems have grown more capable and more brittle at the same time. Let me demonstrate that with an event that had nothing to do with rocks. On the 1st and 2nd of September, 1859, a geomagnetic storm struck. It remains the largest such storm in the recorded era. It is named for Richard Carrington, the British astronomer who observed the flare. Aurora were reported at latitudes remarkably close to the equator. The technological damage concentrated on the only electrical network that then existed. That network was the telegraph, and it was the entire exposure surface. Telegraph systems failed right across both Europe and North America. Operators received electric shocks directly from their own working equipment. Some lines carried live current with their batteries physically disconnected. Paper caught fire in a small number of telegraph offices. That was the total infrastructure exposure of the world in 1859. One wire-based technology, and the event registered mostly as a curiosity. Now move forward exactly 130 years from that event. On the 13th of March 1989, a coronal mass ejection struck Earth. The resulting disturbance index reached minus 589 nanotesla. That is severe, but it sits nowhere near Carrington levels. Induced currents flowed into the electrical power grid serving Quebec. The entire provincial grid collapsed in roughly 90 seconds flat. 6 million people lost their power across the whole province. Restoration took roughly 9 hours from the moment of the collapse. Transformers sustained damage as far away as the state of New Jersey. Hold those two events side by side and compare them properly. Same physical phenomenon and a substantially weaker event in 1989. Vastly larger consequence, because the exposure surface had grown enormously. It went from a single telegraph network to a continental power system. An estimate produced for the United States National Research Council in 2008 quantified this. A Carrington-class event striking the modern grid carries a first-year cost. That cost falls somewhere between $1 and $2 trillion. Restoration timescales in the worst affected regions run to years rather than hours. That trend line is the one that actually matters, and it applies to impacts identically. A Tunguska-scale airburst over Siberia in 1908 flattened 80 million trees. It possibly killed nobody at all, because essentially nobody lived there. The same event over a modern metropolitan area would be historic. The object arriving would be physically identical in both of those cases. The human exposure underneath it would not be remotely comparable. Now here is the point where the timescale mismatch bites hardest. The interval between events large enough to matter is long. Tunguska scale events occur on the order of once every few centuries. Chelyabinsk scale events occur perhaps once in every several decades. Both of those intervals exceed the length of a professional career. The longer of the two exceeds the working lifespan of most institutions. So we are asking organisations that replace their staff every few decades to do something difficult. We are asking them to maintain continuous vigilance against events arriving on century timescales, and to do it using data that only becomes useful when somebody connects it. That is precisely the failure mode I described earlier in this story. It left the Beijing observation unused for 165 years. Let me put an analogy on it, because I think it makes the shape clear. Imagine a house fitted with a genuinely excellent fire alarm system. It detects smoke reliably, and it has never produced a false negative. It gets inspected and tested on a completely regular schedule. That system is the Near-Earth Object Survey Program, and it works. Now imagine that the alarm only covers about half of that house. The uncovered half is the portion you cannot see from the street, and the person who installed the system retires every few years. Each replacement has to work out from the manual what the system actually does. That is not a criticism of the people currently doing the work. The Planetary Defense Coordination Office has grown 50-fold in 2 decades. NEO Surveyor is being built specifically to cover the unlit half of that house. It specifically targets the sunward approach that hid Chelyabinsk completely. That is a serious, funded and competent response to a correctly identified gap. But the fundamental mismatch does not disappear with better hardware. Hardware finds objects, and this hardware will find them well. What hardware cannot guarantee is institutional continuity across 200 years. That is the timescale on which this problem actually operates, and the historical record on institutional continuity is not encouraging. Marsden's prediction failed by 17 days in 1973. The correction came from an amateur working entirely outside the institutional structure. So there is a question I cannot answer, and neither can anybody else. In 2126, when the comet returns and dominates the sky, who checks? Not the people who cleared it, because they will be long dead. That clearance will exist as a number in a database. Those databases will be maintained by institutions that do not yet exist. They will be run by people who have not yet been born. The result will be inherited from a calculation performed in 1992. That calculation used observations recorded in the year 69 before the Common Era. That chain has to hold unbroken for another 134 years. Only then does the reassurance we currently have still mean anything. It probably will hold, and I want to say that clearly. Databases are durable, and the underlying physics does not change over time. But notice what our confidence actually rests on in the end. Our certainty about a 26-kilometre object at 60 kilometres per second is inherited. It rests on the continuity of record-keeping across generations. It does not rest on any physical property of the object itself. And record-keeping is the single most fragile thing human beings do. Consider how much of this story depended on documents nearly being lost. The 1737 Beijing observation survived because a missionary wrote it down. It survived a second time because an archive in Europe preserved it. It survived a third time because William Lynn happened to read it in 1902. The 69 before the Common Era observation passed through 2,000 years of dynastic change. Wars, fires, floods and political upheaval all had opportunities to destroy it. It survived every one of them, and then it mattered. Now think about how our own records are stored today. Orbital solutions live in databases maintained by publicly funded institutions. Those institutions depend on annual budget appropriations from national governments. The formats those databases use will be obsolete within decades. None of that is alarming on a 20-year horizon. All of it becomes a genuine question on a 200-year horizon. The Chinese court astronomers were, by accident, better at this than we are. They wrote on materials that lasted, in a language still readable, and they did it continuously, for 2,000 years, without a funding cycle. There is one more piece I've been holding back, and it belongs here. It concerns whether that object will still be one object. For a long time, the standard model of a comet nucleus was the dirty snowball. That model described ice with dust and rock mixed through it. Then the model shifted toward what people called the icy dirt ball. That version is dust and rock with ice distributed through the mixture. A spacecraft called Rosetta settled a great deal of that argument. It travelled to a comet called 67P/Churyumov-Gerasimenko. It then stayed with that comet for 2 full years of observation. What Rosetta found was a nucleus that is extraordinarily porous. Its density was extraordinarily low, and its structure was very weak. It was not a solid block of anything in any sense. It resembled a loosely bound aggregate held together by feeble gravity. A person standing on that surface would drift off it involuntarily. At first hearing, all of that sounds like reassuring news. A fragile object should break up in the atmosphere and cause less damage. At 26 kilometers across, it does not work that way. The atmosphere is only about 100 kilometers of meaningful depth. A body that size crosses that depth in under 2 seconds. It has no time to disassemble regardless of how weakly it is bound. It arrives essentially intact, and the fragility buys you nothing, but that fragility matters enormously for a completely different reason. It means the object can come apart entirely on its own. Remember what Jenniskens and Vorbayen found about the Alpha Capricornid parent? A fragmentation event 4,500 to 5,000 years ago. Roughly half the mass of the body separated from the rest. Not from an impact, and not from a collision with anything. It simply came apart, because comet nuclei are structurally weak. Thermal stress, rotation, and outgassing are relentless over thousands of orbits. Shoemaker-Levy 9 came apart under Jupiter's tidal forces before it struck. So the honest statement about the parent comet is more qualified than it appears. We have not computed the position of a solid 26-kilometer object. We have computed the position of a loosely bound aggregate of that size, and we did it assuming it remains a single body throughout. We assumed it retains the same response to solar heating as shown historically. If a comet that size fragments during a perihelion passage, every calculation restarts. You would have a swarm of separate pieces instead of one object. Each piece carries its own new orbit and its own newly exposed ice. Each therefore generates its own unpredictable jets from fresh surfaces. All of them travel along a path with a moid near 1,000th of an astronomical unit. I want to be careful because there is no indication this is imminent. Swift-Tuttle survived the 1992 passage entirely intact. It has survived at least 6 documented passages across 2,000 years. The observational record describes a stable and structurally coherent object. But the reason we call it safe is a calculation, not an observation of the future. And that calculation has a load-bearing assumption underneath it. The assumption is that the object stays in one piece. Nothing in physics guarantees that assumption will continue to hold. It is supported by history and by absolutely nothing else. Which is precisely what could have been said in October of 1992. It could have been said about Marsden's original orbital solution. So let me set out the 4 layers of this properly. They operate on 4 different timescales, and they get collapsed constantly. The first layer is the debris arriving in the atmosphere tonight. Its timescale is immediate, and its consequence is precisely 0. It consists of sand grains vaporizing 100 kilometers above your head. This layer is not dangerous, and it has never been dangerous. It is also the only layer that anybody discusses in August. The second layer is the parent body of that stream itself. Its timescale runs from several centuries out into whole millennia. Its consequence, in the worst case available to us, would be civilizational. Current probability is effectively 0 across the next 2,000 years. It rises to roughly 1 in a million at the 4,479 encounter. This layer generates the frightening headlines, and we understand it best. The third layer is the uncatalogued population of small objects. Its timescale is any given decade you care to choose. Its consequence is regional in scale, rather than global in scale. The probability is high enough that it happened twice over Russia within living memory. Every recorded injury in the modern era comes from this third layer. It nonetheless receives almost no sustained public attention at all. The fourth layer is a long-period comet arriving on a first passage. Its timescale is entirely unknown and cannot currently be estimated. Its consequence would be catastrophic, without any qualification or hedging whatsoever. The probability of it happening in any century is genuinely low. The warning time available to anyone would be measured in months. The available response, using everything we currently have, is nothing. Compare how those four layers rank by attention against how they rank by exposure. Attention concentrates almost entirely on the first two layers I described. Those first two are respectively harmless and extremely well characterized. Layers 3 and 4 carry the actual exposure and receive a fraction of the coverage. That is nobody's fault, and I want to be fair about it. It is a structural property of how information moves through a population. Layer 2 has a name, a number, a date and a quotable book. Layer 4 has none of those things and cannot have them. There is a final piece of this I want to place before the close. It concerns what happens to attention after a scare resolves. In 1993, the year after the retraction, coverage of the comet collapsed. The story had an ending, and the ending was reassuring. Editors moved on, and the public moved on with them. But the scientific work did not stop when the coverage did. Orbital solutions were refined repeatedly across the following 3 decades. The uncertainty on the 21-26 approach kept shrinking. It went from a 15-day window down to 10,000 kilometers. That work happened in silence, funded modestly, watched by almost nobody. It is the reason we can speak confidently about the object today. So the reassurance you have been given in this story was not free. It was produced by people continuing to look at something after everyone stopped caring. Hold that thought carefully, because it is where all of this ends. You cannot write a headline about an object that has no name. Part 17. The moment everyone stops watching. 11 nights from now, 3 streams of debris will be crossing our path. The fastest of them arrives at 59 kilometers per second. Behind that stream sits an object 26 kilometers across. Its orbital path passes within about a third of the moon's distance of ours. I opened by asking whether we proved that comet is safe, or whether we merely stopped being able to see the danger. Here is the most honest answer the evidence allows me to give. The calculation is sound, and I have no reservations about saying so. The 2,064-year observation arc is real and verifiable. The uncertainty on the 21-26 approach is smaller than this planet. The object is not on Sentry, and it does not belong on Sentry. Anyone telling you a 26-kilometer comet is coming in 21-26 is wrong. They are either misinformed, or they are quoting a document that was withdrawn. That withdrawal happened 8 weeks after publication, 34 years ago. And here is what I cannot tell you with any confidence at all. I cannot tell you we would know any of that without one man's hobby. Gary Kronk held no professional position and answered to nobody. He spent his own time reading 2,000-year-old Chinese astronomical records. He noticed that 2 of them fit an orbit nobody had connected them to. Nothing about the comet changed during the autumn of 1992. Its orbit in December was identical to its orbit in September. The mass was the same, and the velocity was the same. Only our understanding of what we already possessed had changed. Our safety, in that instance, was not a property of the solar system. It was a property of somebody paying attention to something nobody had asked about. And that generalizes in a way I find difficult to sit comfortably with. Every object in the catalogue is safe because somebody located it first. The catalogue is not a list of threats waiting to arrive. It is a list of things that have already been checked and cleared. So the size of the danger is not set by how many dangerous objects exist. It is set by how many we have not yet turned a telescope toward. Consider Tunguska again, arriving in the summer of 1908. It flattened 2,150 square kilometres of forest and 80 million trees. It arrived with absolutely zero warning of any kind whatsoever. Consider Chelyabinsk, arriving over a Russian city in 2013. Weigh these three cases against one another one final time. It injured 1,500 people and damaged 7,200 buildings. It gave zero warning because the object arrived out of the sun. Consider 2019 OK, 100 meters across, passing inside the moon's orbit. It was found on the way in, with only days to spare. 3 events, and not one of them carried a name beforehand. Set against that, one object had a name and a date and a book quotation. That object turned out to be entirely fine after all, and we know it is fine precisely because it had a name. The objects that carry names attached are always the safe ones. That is not a coincidence, and it is certainly not luck. That is simply what the word named means in this field. So when the coverage runs next week, and it will, go outside anyway. All of the advice will be accurate, and the recommendation is a good one. This year the moon is out of the way entirely. But understand what you are actually looking at while you lie there. You are watching the exhaust trail of a mountain of ice. You are watching material shed from an object twice the width of the dinosaur killer. It is arriving on a schedule that predates agriculture on this planet. And it arrives on a night when 3 unrelated cycles happen to align. Coverage of impact risk arrives in spikes, and then it stops. An object gets a number and a probability, and headlines run for 2 weeks. The probability then collapses to 0, as it almost always does. The coverage ends, and everyone moves on to something else. The structural effect of that cycle is to teach people something false. It teaches that these stories always end in nothing at all, which makes the next one very slightly easier to ignore. But the risk does not run on that schedule, and it never has. The risk is flat, continuous, and completely indifferent to our attention. It does not spike when a story runs, and it does not subside when coverage ends. It is the same tonight as it was in 1992. Minus the objects we have found across the intervening 34 years, plus every single object out there we still have not found. Swift-Tuttle was never dangerous in the way those headlines described. It was dangerous in the only way that has ever mattered. For 8 weeks in 1992, the honest answer was that nobody knew. And what ended those 8 weeks was not a discovery in the sky. It was somebody paying attention to something sitting in plain view for 2,000 years. There are objects out there tonight that nobody has looked at yet. There is no circular carrying their designations, and no probability attached. There is no date, and there is no quotable line in any book. They are not frightening to anybody, because they cannot yet be named. The most dangerous moment is not the night the sky fills with light. The most dangerous moment is the night after everyone stops watching.